Everybody good? How about any follow-up with regard to yesterday? We've got a couple minutes before our speaker comes on at 9:15. Any follow-up with regard to anything we covered yesterday? I thought you all did great with the role play and the case study analysis. And I think listening to the videos was a lot of fun to see the different personalities. How about any follow-up with regard to that?
David, I got a quick question. Well, it may not be a quick question, but it's a question. Okay. So, we have all these different personality types, and we try to bend towards those personality types so that we can relate or that we can communicate on their level, right? But at what point do you draw the line to say, how far do you bend to accommodate a sentinel versus another personality type? You know what I'm saying?
I do know what you're saying. I'm going to give you an analogy. So let's say that you go to Japan to do business, all right? And you've got to learn the language and you got to learn the customs so that you can interact with them. So even though you develop skills to interact with them, you don't sacrifice your business objective. So what you're doing here is you're acquiring tools and skills that are going to help you more effectively connect and engage with that other party and move them from where they are at point A to where you want them to be at point B. So even though that you're doing all of these things, you can't lose sight of the fact of that line from A to B and what the point B objective is. That's what it's all about. This is about using leadership power as opposed to force. Because previously, you look back at the Middle Ages, when we had a feudal economy, and many countries we had slave economies, and you used force. You basically said, "Go do that job. I don't care who you are or how you feel about it." So today we're in a different world. Today, leaders attempt to use power. Some leaders use force. You had Al Dunlap, who was with Sunbeam, and he basically came in and just got his machete out and hacked anyone and anything that he wanted to. That was using force. Today we try to use leadership power, and these are fairly sophisticated behavioral tools that we're sharing with you. They're not always going to be effective. You're gonna make that attempt to engage and connect and move those people agreeably along from point A to point B, and understand how you all can get to point B together. But you can't lose sight of point B. Does that make sense, Matt?
Yes, sir. Thank you.
Yeah. So, and I see that Christina is with us now. Christina, are you online? You want to give us a audio and a video test?
Sure. Took me a second. Haven't used WebEx in a while. Good morning.
There she is. Yeah, good morning to you. So, your video is just crystal clear. You must be on a hardwired Cat5 cable or something. And you got good internet over at the university. I assume you're at the university right now.
Yeah, I'm in the office.
Super. Today. Yeah. So, well, let me, if you don't mind, we'll get started a little bit early.
Sure. We may finish a bit early.
All right. Well, that's no problem. We'll just give a little bit longer break. So I'm going to give you a brief intro, and then I'm going to turn the program over to you.
Sounds good.
If you have any problems with the technology, just raise your hand, because both Jess Buchanan, E4 Carolina's administrative manager, and I are going to be online every second. So Christine is the program manager at the Energy Production Infrastructure Center at UNC Charlotte. She manages their EPIC Affiliates program, and that's a partnership between industry and academia. It focuses on workforce development, and it attempts to get new advancements in energy, bring in new advancements in energy as it educates the graduating workforce. So she, before she joined EPIC, she was still in North Carolina. She was a clean power industrial efficiency specialist over at the North Carolina Clean Energy Technology Center at NC State. And there she focused on CHP, waste heat to power, and other clean energy technologies. So she received a Master's in Science of Sustainable Energy from Andover University of Technology in the Netherlands, and also a BS in Mechanical Engineering in Athens, Greece. So that is our Christina. delighted to have you with us. And Christina, I'm going to step back and let you talk the people through. Oh, let me take just a minute. I'll give you just a little bit of an idea as to who's online with you. We'll talk you through some of these folks. So we have online energy professionals from Framatome in Canada, actually, Siemens Energy, Carolina Gas Transmission, which is natural gas, the natural gas side of the industry, from Electricities, from Central Electric Membership Corporation, so Electric Cooperative, Westinghouse, ClearPath, which is a clean energy advocacy organization, the Electric Power Research Institute, City of Charlotte, Duke Energy, Pillsbury Law, North Carolina Advanced Energy Corporation. I know you're familiar with them, and RNG Futures, which are renewable natural gas. So you have a real variety of people online with you. And I know that they're interested in energy research at UNC Charlotte. So Christina, the program's yours.
Okay, well, thanks, David, and good morning, everybody. I'm glad everybody is here today. Would be better if you were actually physically here today, but you are always welcome to come and visit EPIC if you have the opportunity. We love people coming in and seeing, the work we do here and the facilities. So as David mentioned, my name is Christina Kopitopoulou. I'm a program manager here at EPIC, and I really have been focusing on workforce development for the past few years. I came to EPIC in 2016. So I have been working with companies like yours, and a lot of them are your companies, to kind of, work with the students here and see how we can get them more engaged in the energy industry and interested in the energy industry. We really focus more on the engineering students, but all students from the university that are interested can come and talk to EPIC folks to kind of get more engaged with the energy industry. So I have a presentation to share, and since David did the introductions, I think we can jump right.
EPIC stands for the Energy Production Infrastructure Center, and we are a university research center that is part of the College of Engineering at UNC Charlotte. We are doing our part to change the energy economy, and that means changing almost everybody's way of life.
I think EPIC is different than other energy centers across the state, across the country, because of our industry focus.
We are focused on the energy needs of today and tomorrow across all the disciplines that are required.
For students, there's a tremendous opportunity in the energy industry. Who care about technology, want to be on exciting field where there's a lot of action, a lot of opportunity for their entire career.
One thing that made me pick UNC Charlotte was the emphasis by EPIC on energy research.
The main reason why I came to EPIC was the kind of unique style of the facility, which combines every type of energy research.
This is an exciting time to be a student in energy. Everything about the energy ecosystem is changing. And so all of that disruption means the companies that are involved in that will need new perspectives. They'll need new skill sets.
So EPIC has a number of well-established labs which are unique in many ways.
What EPIC provides is that infrastructure which allows our potential partners, our existing partners, to conduct performance testing of new technologies. Also to conduct pre-certification testing of new technologies.
We are very heavily focused on being responsive to industry and the fact that they work on a different time scale. It's very good for our students to get the exposure to industry projects and really gives them good exposure to the kinds of things that they'll do on the job.
Technology and energy has just exploded on the scene. And it's not going to stop anytime soon.
To stay at the cutting edge of technology, to be looking out into the future, to identify needs that people aren't even aware of yet, where we can start making progress in those areas and be ready for the future before it gets here.
Okay, well, that was choppy. That's okay. Then we got, oh, there we go, the overview. So EPIC stands for the Energy Production Infrastructure Center. We are part of the College of Engineering here at UNC Charlotte. So the idea of EPIC started around 2007, 2008, when the industry in the Charlotte area, the energy industry, started to talk with the university here about the lack of new engineers coming into the energy industry and how really, you know, their workforce is getting older and they see the engineers retiring, losing the experience, and not enough new engineers coming into the industry. So an effort was put forth with a lot of the companies around the area and the university to really go to the legislator and ask for funds to build a center that would focus on energy. So the legislator awarded $78 million to UNC Charlotte to build this facility and hire faculty that focus on energy. We finished the building in 2012, so it's a fairly new facility in the university here. So with that, you know, the industry is getting older, if you will. The engineers, especially in the industry, were getting older, and new innovation was coming in, and they wanted people to be trained for it. The center was created. The idea was not only to have students, like our younger students, but also offer professional development for existing employees of the companies to kind of get in touch with the technologies that we see coming through or being applied that are, you know, not your typical day-to-day operations, if you will, in the energy field. So we really focus on applied research. Energy is the only thing we do. We don't really do anything else. And the idea is, how can we make sure that we have safe, reliable, and sustainable energy for the future? We work with a number of universities within the Carolinas, but also abroad. Our more noteworthy partnerships, if you will, is with NC State, Clemson, and then the Karlsruhe Institute of Technology in Germany. So I'm going to talk a little bit about those things further down. So the founding mission was really, you know, to get that center going, but then the continuing mission that we have here at EPIC is obviously education and workforce development. So how do we attract more students to the energy industry? How do we make sure that we facilitate, you know, and support experiential learning? Make sure that we also attract graduate students to research. So once we've done with undergraduate students, how do we get more students interested in continuing and you know, going on and doing their masters or PhDs? And of course, we have what we call the Senior Design Program, which is your capstone program that every university has. So ours is a little bit different than most. About 75 to 80% of the projects are sponsored by industry. So the students really get the opportunity to work on real problems that the companies are facing, that they're trying to solve. So how do we make sure that we have enough of these senior design projects that are energy focused and get the students to work on those? And then, of course, we do program development with other regional universities. We work together with different organizations like U4 Carolinas, the Research Triangle, and a number of other energy-related companies and institutions. So research and development, we do applied multidisciplinary research. So we try to work not just with our engineering facility here in the engineering department, but also with the other departments of the university. So we have really good collaborations with computer and informatics, for example, with geography, the business school. So we try to make sure that when we're looking at research projects, we are not only looking at the technology, but how does it all kind of fit together in a more holistic way. We do a lot of corporate engagement. We were funded and founded by companies, so we still work a lot with corporate companies. We leverage government funds, of course, like every good public university, and we try to get that cross-campus participation throughout our campus itself. And And then, of course, as I mentioned before, we do work with national and global universities, and of course with a lot of the national labs here too within the US. We do a little bit on economic development. So we also have Venture Prize on campus, which is more of a not really an incubator, but what they do, and I have a slide on that later down the presentation, is take the ideas that come from campus and see how can you kind of get them out to market. So we, as most centers, have an external advisory board. Our chair for the advisory board is Thea Jamil from Duke Energy. And I'm sure if you go down this list, there's a lot of people you probably know of, heard of, and a lot of them are from your own companies. So our advisory board is very involved. They really look at kind of the direction that EPIC is going and offer advice about what they see, the needs they see in the future, and what best way EPIC can kind of work around the problems we see to make sure that we are positioned to really help further down the line. So I have structured this presentation a little bit between workforce development and then research, and in the middle I have a tour. So we're going to start with the workforce development part, which is really for EPIC itself as the affiliates program that I manage. Of course, we work with the College of Engineering to work with everybody that is interested, but the affiliates program is really specific to its members. So I'll get into some information about that. So again, if you have any questions, just feel free to interrupt me. So the college itself is about 60 years old, and here we have the engineering disciplines of civil and environmental engineering, electrical and computer, mechanical, systems and engineering management, and we also have engineering technology and construction management. So overall, last semester, we had around 3,660 students, the majority of which are undergrads. Around 3,172 students are undergrad, and then 488 are at the grad level between both masters and PhDs. I was looking at the statistics to go in and give some more statistics about, and I started looking at, what is really the composition of female to male students, and the numbers were exactly the same as undergrad and grad. So that was a very interesting way of splitting the students, but around 14% of our students are female, which is kind of where the national average is for engineering. We do try to get more students involved, more diverse students involved, and I know the university is doing a big push about, seeing how do we get more students and more diverse students involved in engineering. The EPIC Affiliates program itself is a membership program. We offer different tiers of membership from $50,000 at the highest level to $5,000 at the lowest level. But really what we're trying to do is focus on workforce development. So we're trying to kind of enhance the workforce by supporting educational and experiential learning. We're really about experiential learning at UNC Charlotte. We want to make sure we provide a structure to connect our affiliates, our members, with the students, but also with the faculty expertise. And we have what we call, for our engineering program, we have the energy concentration. So there's different concentrations in the different departments. Energy is under all departments, so both civil, mechanical, electrical, all of them have the energy concentration. Which means that the students really select their technical electives from a list that has an energy focus. So with that, we know, which students are more interested in energy. We make sure they kind of take the courses that make sense for them. And we make sure we try to connect them with, the companies so they can do different internships and things like that. We work also with national labs a lot, and we have, different companies have different needs about what kind of students they can hire. So we want to make sure that we have a variety of students that are, for each situation, if you will. So if a company really requires only citizens, there's enough students here that can do that. If they are looking at a more diverse population and they're trying to get diversity more in their employees, we help them with that too. And, a lot of the companies here in the Charlotte area are global companies. So we want to make sure that we have that connection also, and that our students are not only focused here in Charlotte and not only think about Charlotte and the Carolinas, but get more of a global perspective, if you will. So these are our current affiliates. So a lot of your companies are part of the affiliates program already. If they're not and you're interested, you can always email me. So that's my self-promotion and right there. So the main benefits of the program are really focused on kind of three different things, if you will. So we do a lot of brand recognition for the companies that are not as known as, Duke Energy and EPRI and Siemens. But besides that, we focus then on a lot of career fairs and events, and then we do a lot of projects too. So we make sure that our companies participate in different career fairs and networking opportunities with the students. We make sure we get the right students there too. As I mentioned, the energy concentration students is really what we focus on. We do help our members get their internships filled with students. So this can be at a very one-on-one level. So we get the internship opportunities, and they tell us where we're really looking for students that have, X skill set. So we work with the faculty to identify these students and make sure that they at least apply for these internship opportunities. And we do anything from your typical kind of summer internship opportunity or a full year, internships, to anything to short-term projects, like a couple of weeks or a month. So we've done a few of them with EPRI specifically, or in Siemens. They'll come and say, well, we're looking for a student that has this specific skill set because, we just need some help on that. And that works really well for them too. We have what we call the Epic Innovator Competition. I got a slide on that. We also started a mentorship program. So we get folks, engineers mostly from the companies that we work with, to mentor students that are interested in getting that connection and get mentored on, energy industry. And then on the project side, we have the senior design projects, like I mentioned. We have what we call seed projects, which are kind of your lower dollar, if you will, so around $30,000. They're not really very expensive, if you will, projects, but there again, they're all done by students, so they get that experience in research and in working with the companies. And then we have our exchange program with KIT, which I got a slide on that too. Yeah. So the Epic Innovator competition is interesting to us, not only because we get to hear about ideas that students have about, and it could be anything from just an idea, it could be concepts that they've already developed, prototypes. So we get a variety of students that apply to that. But to us, it's also interesting because you see which students are willing to put themselves out there and talk to the companies and present to companies. So that's another tool really for our companies to get to know students and hire them outright, if they're interested. So this is in collaboration with Ventureprise, as I mentioned, which is really there to provide Charlotte's campus with entrepreneurial fundamentals, especially the students. How do you go about taking your idea and making it more than what it is? They do a lot with market research. They have a number of programs from NSF and DOE where they offer funding for the students to really go in and, think about their idea, but not just the technology side, but really more the business side, if you will, of things. I've got the website there. And if you are interested in anything more and you're not sure, just, shoot me an email. My contact info is on the presentation, and we can connect you with the right people within the university. So, good. Okay. So the competition is structured where we get 5 teams are selected by the industry companies that we work with. And then they get a mentor from the companies, which helps them within a 3-month period to really kind of prepare for a presentation. Then the presentation is completed. Again, we have a panel of affiliates that judge the ideas, and, then we give them the awards. It's $1,000 for first prize and dinner used to be dinner with one of the companies. Now it's not really like that. We hope that next year we can do it that way too. And I just put here kind of who the winners were the past 2 years, just because it shows kind of the variety of projects that we're looking at. And we try to kind of get not only PhD students, so we get a lot of PhD students, right, because they have kind of, they're at that point, they're working on a specific idea, on specific research, but we get a lot of undergrad students too, which will come with like, well, what if, ideas. And it's interesting to see how different they are and how they really kind of develop between the undergraduate students and the graduate students. And we have winner from all, so it's not like the industry that is judging them is really just focused on in-depth research. They look at it more holistically again. So we have also the exchange program with the Karlsruhe Institute of Technology. So this has been going on now for probably about 8 years. So each year we get graduate students from KIT to do spend 6 months here at UNC Charlotte. They work on a specific research project with industry and or just faculty members. And then we have our students that go to Germany for 3 months during the summer, just so they don't miss really their semesters, and work on our research projects there. So we try to get our students more engaged with, globally, if you will, and interested in going abroad and seeing how research is very different, actually, how it is completed in the US and abroad. And I think that really gives our students a very different perspective. And our faculty that work here with the KIST students always, they like to see how they think a little bit differently than our students here. So it has worked very well. And this now it's going beyond the student exchange. We are starting to do a little bit of faculty exchange, but also projects that are being worked on at the same time. So if you look at the example project, the first one is a project that one of our students is going to be working on this year at KIT, though it's going to be kind of half virtual, half in person. We hope they can get to travel later in the summer. And then the second project there is actually a collaboration with Siemens, and that's where a KIT student is going to be working with that project here. And the third project is actually a combination project with faculty from both KIT and here at UNC Charlotte. So just some examples there. So with the EPIC labs, I hope this is going to work. So we have a number of labs here. Some is what we call our core labs, which are really more not assigned to a specific faculty member. So in the university, you typically have labs, and they really belong to, to one professor that is really doing a specific type of research. So we have a number of labs that are really beyond, they go beyond that, is really focused for interdisciplinary research, and they are available to all faculty to work in, and, depending on the work they're trying to do. So we have a tour that I hope is going to work. But we're going to look at some of the labs. We're going to look at the high bay, the flexible energy lab, the smart grid lab, and the large manufacturing and the PV lab. So I'm going to pause for a second to see if there were any questions up to now. No, we're good? Okay. So let's see if this is going to work. Come on, load. Okay, so you can see that 360. Okay, good. So that's the outside of our building. I don't know if anybody actually graduated here at UNC Charlotte, or if you've been on campus at all or not. So if you actually were here, this is where we would be meeting. So this is really our lobby. Our main office is on the left there. And typically when we have these types of meetings, we do them in a big boardroom, which is on the right there. But let's go and take a look at some of the labs. And this is on the website too, so you if you want to kind of go and explore things, you can do it yourselves too. So this is our high bay lab, and typically when we do, when we have this group here and you go about the labs, we have the lab managers there, and they can offer a lot more information about the labs than I can. So again, if you see something and you're interested, or if you want to get more information, I think I have most people's information on here, but if not, just, shoot me an email and we can get you connected with the right people. So this is our Have-Bay lab. It is really a let's see if this is going to work well. Oops. Okay, so this is a 3-story building pretty much. So we have, here is a strong wall. So this is a 32 feet high strong walls. So this can withhold a maximum of 1 million pounds of shear force. So the idea is really that they can, connect with their equipment here with these actuators and kind of test them. So a lot of the tests they do here have to do with testing large structures and components. We have in here, parts of walls, or, we have parts of substations and things like that. So a lot of the work they do is really kind of going in here and seeing how they can break things. But a lot of the work they do is also with verifying numerical models, taking models that have been created and looking at them on the experimental side of things. They work with a lot of the companies also to kind of improve industry standards. There was a project we're doing with EPRI, and that was a multi-year project that really was focusing on the new composite insulators and how they react to if they get damaged or if they break. So how do they really react, and how would we develop an industry standard, because that does not really exist yet. So we have, and I think we can go down. So that was a strong wall. The floor too is a 6 feet thick floor, strong floor. So these little squares down here, you can pull them out, and that's how you connect whatever you're trying to connect to the floor. And I think we have here, let's see if this is going to work. Okay, so that's in slow motion. So really what they're looking here is simulating an explosion. That is just really a piece of glass that is there. It's just painted, so they can see the fragments with cameras that they have around this experiment. So the idea was, how do you simulate an explosion, and kind of where do all the pieces go once something has exploded? So they did that with creating a vacuum behind the glass there and just exploding it. So it's always much more fun when our manager does these presentations, because he goes in a lot of detail about all the different things they were looking at. But that's fun. And then in slow-mo. So this is a project that all our civil engineering students have to work on. The idea is to design a beam, and they don't need to design the strongest beam. They can select the materials and kind of the structure of it, but the idea is for them to be able to calculate when it's going to fail. So, they do the theoretical part and the numerical analysis and figure out, okay, with this force, that's when it's going to break. And then we actually make it and break it and see how close they were to, how good their estimation was about failure. So again, this just has to do with, making sure that students understand what they do in theory, how it really translates, into real life. So this one is testing a different type of concrete. So this concrete has fly ash mixed into it. So it's a different chemical composition. So what they're testing there is its strength to compression, which apparently was really good. So this is just going to go on forever, this video. But these are kind of the types of, experiments or research that's going on at the High Bay Lab. It's typically usually about breaking things. So every time there is something going on, everybody wants to go and see, what is going on there. It's always fun. Okay. So that's the part of the High Bay. And if we go upstairs here. So we also have here two 30-ton cranes that were donated by Westinghouse when we built the High Bay Lab. So they can really kind of, go in and lift much heavier structures and really test them in different ways. And I just wanted to go through here. And when you break things, you typically want to be behind the glass. You don't per se want to be down there. So we have, a control room where they kind of look at all the different things that are happening down in the High Bay. And I think here there was another little video. So the High Bay also has two pits. There's a round pit right here, and this is a square pit. They're about 10, the round one's 10 feet deep, and this one is divided in two parts with a 10 feet deep and a 5 foot deep pit. So what they're doing here is a geotechnical project. They are just kind of driving piles into the soil they have here. So they have, again, designed some type of soil, different composition of the soil. What they're trying to see is how it reacts when you drive the piles in, and kind of the strength of the soil and things like that. So these piles are fully censored, if you will. They're full of sensors, and they're trying to figure out, how it all kind of works out. And again, this has to do with obviously construction, right? You're looking at foundations, things like that. We used to call it our tree pit here. So there were tinder poles from Duke Energy, about 6 or 7 of them in this pit here. And they were doing some research about creating a sensor that could indicate whether the pole was structurally sound or not. So, the timber poles are out there. They're getting to the time where they need to be replaced or should be replaced. But the question really is, how many of them are still okay for a few years, and some are, really rotten inside. They've just deteriorated. So the idea is to create a handheld type of sensor that can use vibrations and thermal profiling of the pole, if you will, and to see, in what kind of state it is, and just more to say, okay, this is a pole that a technician can actually climb or shouldn't, and it should be replaced immediately. So we don't have our poles there anymore. They're beyond that point, but as far as I know, that has been going pretty well, that project. Okay, so since we're up here, let's see. So, all right, let's go to the Smart Grid Lab. So this is our Smart Grid Lab. It's called the Duke Energy Smart Grid Lab. It was funded partially by Duke Energy. So what we have here is, scroll this way. All right. So a lot of the work we do here has to do with real-time simulation, and a lot of it is really just kind of emulating the grid and looking at how different components would work on the grid. So a lot of the work we do here is with utilities, looking at integration of renewables or devices specifically. So we have here 3 RTDS racks, which are real-time simulators. We also have an Opal RT rack, and here we have a number of breakers and other devices, and most of all of SEL for Schweitzer Engineering. Then this here is also a 90 kVA amplifier, so we can do hardware in the loop testing. So typical projects here are really, we would start with students, for example, creating some kind of model or taking a model of the grid that a utility would provide, simulating it, and then running it through the real-time simulator to see, if you connect, for example, a solar farm or you connect a wind farm or whatever, how does that affect the grid? And then we can also really actually connect real hardware with the amplifier to see how that would react. So I got my cheat sheet here. So some of the things that they have been working to is also a lot of controls. So control hardware and software devices to test communications with the real-time system studies. They do a lot of work with relays, power converters, smart meters, etc. The lab also has its own server because a lot of the data we get is, company sensitive, if you will. So it has its own server, and it has it is also, this lab is connected to the Flex lab, which is the one we'll see right afterwards. So this is more on the simulation side, very small, system or very small equipment, and then we can go downstairs. So this is what we call the Flex lab, just because it's set up to be able to be configured depending on the testing that needs to happen here. So it's kind of divided into 2 parts. One is the large manufacturing side, which we'll take a look at in a minute, and then we got this side, and I wish they had, you can't really see it really well, so this has a test bed for both cables and wires. Like you see here, there is this cable. So the testing that we're doing on this is kind of looking at thermal properties of the cable once you go beyond its rated amperage, to see kind of if you go above for X amount of time, how does that react, kind of what thermal properties develop within, the cable itself, would it fail, things like that. So there's that test bed there, and it also does high voltage insulation tests rated up to 100 kV. And then the load here and the conductors are up to 4,000 ampere. That's part of it. And then the second part of this lab, whoops, wrong way, is on this side. Okay, so this really, what we have created here is a one MVA grid simulator that includes a 4160 volt medium voltage test bed. So this is the front end rectifier here, is connected to the grid. So what we do, and there's 2 inverters, and you can only see the one here, and we can't unfortunately go on that side. But really what they have is 2 inverters, one's leading, one's following, and they've created pretty much a grid within it, if you will. And they can test devices. So a lot of the tests they will do here now has to do with pre-certification often. So companies that have, created an inverter, for example, or a motor or whatever, and they need to test it before they go through maybe UL certification or something like that. They can come here, test it as it would be, before they need to go and do the testing to get certified. We've also actually had people from UL come here and certify specific, equipment too. So this is what this is on this side. And I'm looking at the time. We're till 10:30, I think, right?
So I'm checking. You're good until 10:30,
Okay, well, we won't go till 10:30.
but you can.
Just make sure I'm not like, taking too much time over our part. So that is kind of the work they do here on that side. And let's go to the bit of a different angle from there. And I was going to say, here it is open right now. That's why the cage is not around it, but typically there is a cage around all these things. So it's not that you can just walk in if something's going on. So this is what we call the kind of Siemens Large Manufacturing Lab. A lot of the work they do here is really metrology based. So this is I think it's called, let me look at my cheat sheet here. It's a LIGHTS PMM coordinating measuring machine. So it's a precise measuring machine. So what they do, a lot of the work and research they do here is really getting parts of large equipment and creating an accurate measurement of them. This goes down to a couple of microns, I think. Yes, and micrometers. And then it sits within its own enclosure, as you can kind of see from this side. So it's also kind of temperature tested to make sure it's around 20 plus or 5 minus C, that's 68 Fahrenheit. So it sits on its own foundation. So this is a very large, heavy granite piece of equipment. It sits on its own foundation to make sure it is insulated by vibrations from other things happening in the building itself. Before they do any measurements here, they'll bring a piece in, leave it for at least 24 hours to make sure it's at the right temperature, and then start the measuring process. Things that we'll do with, we typically do a lot of work with Siemens here. Before this machine was here, which was donated by Hexagon Metrology, Siemens would send parts to Germany to be measured. So now that this is here in Charlotte, and that's why it is here really, it's because Siemens worked with Hexagon to kind of bring this machine here at UNC Charlotte. They get the opportunity to bring parts of turbines, for example, maybe something has failed in the field or just something that is now being created, to really profile it and make sure, how it is working, make sure it's working correctly, or if it failed, maybe see why it failed. We have a very large precision metrology group here at UNC Charlotte, the College of Engineering. So besides this machine here, there is a lot of other precision metrology equipment, but they're not in the EPIC building. They're in a different building. So that's a lot of work that's being done here. Let's see if we can get out of here. So then on this side, we also have a 5-axis CNC machine. This here is a Moriseki. So a lot of the research that's being done using this specific equipment is with gears. So designing new types of gears and making or smoother profiles of gears. And so a lot of times, they will make something here and get it measured in the other machine. That's more on the precision metrology, really, side of things. So since we're down here, I hope I'm not making anybody too dizzy going back and forth like this. We also have a PV research lab. Okay. So this is a full-scale manufacturing facility for PV panels. We obviously only use it for research. We're not making and selling panels. But a lot of the research that's being done here is more on it's not on the silicon wafers or anything like that. It's more on the configurations, if you will, of the panels themselves, the arrays. So the panels, so you're looking at really the buses and lines that, that are kind of printed on top of the wafers, different configurations and how kind of you can see if you can get better efficiencies, things like that. So what will happen is they will get these silicon wafers, they get them, okay. So we get them empty, so it's just a blue wafer. They look at what kind of design they want to have. Then it goes into this machine, which is a printing screen pretty much. So it has a module, it prints on that blue wafer the buses and lines that you have designed, and then it goes through this machine, which is just a pretty big oven, really. So this here is kind of the temperature profile. So it's very high temperature for a very short period of time to make sure that the metals don't diffuse once you print them, once you bake them pretty much. So then, you know, it goes through this machine, comes out in the end, and you have things that look like this, which is the printed material on the wafer. Really the work that is being done here is more on the manufacturing side, maybe looking at different metals for you know, to be used, but really not on the chemical side of things. That is not what's going on this side. So that is our PV lab. Let's see if I'm missing anything. And then maybe another one. Where are you? I know you're in here. There should be an easier way to do this, but there's not. Anyway, so we have another lab. You can't really see much when you go in. Just a number of boards. They do a lot of research on inverters. So smart inverters. We have outside. We have a solar roof, if you will. So we have a port, a solar port, that is connected to that lab, and they do a lot of inverter research and testing. So connecting it to the solar panels, to those inverters that they're looking at, and kind of getting the details into the lab and the data. So that is, I think, the tour, if you will. Let's see if I can go back to the presentation. Okay. So again, if anybody is, you know, if you're ever in the area, if you live in Charlotte, if you're interested in actually seeing the labs in person, you're welcome to. We do often, you know, have tours for folks. So that's always an opportunity. And the lab managers can give you a lot more information, obviously, about what's going on in the labs and what projects they're really interested in, right? So I wasn't sure if that's going to work. So these are just, I'm going to go through these. Come on. And you're going to share these presentations, right, David?
We will share the presentation.
So,
as long as you provide it to us.
Sure. Yeah, I don't think I have yet. So this is a bit of a better kind of way of looking at all that stuff. Okay. Oh, that's from the outside. Come on. Okay. Oh. Stop moving. Okay. So, so as I mentioned, you know, all the research we do is really energy related. What is a little bit different between EPIC and your typical university center is that we are heavily industry funded. And that's the only reason why I have this slide up here. So most other universities, you know, maybe there is a 20% that's industry funded research. We are really at about 40 to 45%, depending on the year, which is kind of a big chunk of kind of the research project we do. And again, the difference between those and, for example, the federal chunk here is that this is typically comprised of a lot smaller projects, right? The industry projects may be more in the couple of $100,000s, where then if you're looking at some federal grants, you know, they're about $1 million or more. we did get some big grants in 2020, and that the slide is not outdated. So I think now we're around $80 million in funded research overall for EPIC. So this is just kind of a slide just to kind of to show kind of the different types of funding that EPIC receives. So as I mentioned in the beginning, or did I mention at the beginning, we have around 20 faculty members that are, energy focused faculty. So a lot of the work they do has anything to do from systems level, like grid systems level or devices. A lot of the work that's being done has to do with integration of renewables or EV infrastructure, coal ash work, resiliency, and so forth. So everything is kind of grid related. We've got a big power electronics group, so a number of faculty that work power electronics for the energy industry. And that kind of brings me to this here, which is another center that we have here at EPIC, and this is a collaboration between Clemson, NC State, and EPIC. For the kind of academic side of things. It's called Center for Advanced Power Engineering Research, or CAPER. It's another membership consortium. It was really the birthchild of Steve Wisnant from Duke Energy. And the idea was, how do you get initially utilities, but then it's kind of open to different companies too, and the universities to work together on combined research projects. And again, trying to focus really on what the issues that they see in the industry and the power industry, and how do you kind of help solve it. So this is another way of, again, collaboration between different universities and industry. And CAPER has been going on for 7 or 8 years too. It was initially the first 5 years, NC State was the lead university. Now it's us here at EPIC. And then once we've done our 5 years, the next 5 years we'll go to Clemson. So again, it's kind of trying to go around the universities too, and also not just stay at the same place all the time. So I think after this, I have a couple of examples of research projects. If you're gonna, okay. So I have 3 projects examples, and that is just kind of to show the different types of work we do. So this one is called Planning an Affordable, Resilient, and Sustainable Grid in North Carolina. So this was a competitive award from DOE to the state of North Carolina. So DEQ, the North Carolina Department of Environmental Quality, got this grant from DOE to work on a roadmap about kind of looking at resiliency for the state of North Carolina. So DEQ partnered with EPIC and with the North Carolina Clean Energy Technology Center at NC State University to kind of look at this project. So it really examines storm-related impacts and the cost benefits of investments in grid resiliency, as recommended of the North Carolina Clean Energy Plan. So I'm not sure if everybody is, not everybody's from North Carolina, so not everybody will know about the North Carolina Clean Energy Plan, but it has set very ambitious goals about the state and its generation mostly, but also, kind of the emissions and reductions of greenhouse gases. So the goal of this project is to develop a roadmap that will help inform key energy planning processes. And also, beyond that, looking at how can, for example, the Utility Commission or others take this information to make sure that policy is also where it needs to be able to implement things like resiliency. So EPIC is working with Duke Energy. Duke has given us outage data from 15 to 18 to conduct a power system cost benefit analysis. So kind of we're looking at storm impacts in 3 different scenarios. Then the Clean Tech Center has led stakeholder processes to kind of get, stakeholders involved throughout the state of North Carolina, whether it is the utilities themselves or, communities, cities, just industry, manufacturers, etc., and get input from them. And then DEQ will take the findings and kind of incorporate them into the state risk assessments and resiliency plan, and also see how they can coordinate with the results of this to develop state hazard mitigation plans for maybe not just North Carolina, because DOE is really involved in this project too. So they're trying to see, kind of the results that are going to come out for this, and could you take those and implement it in other states too. So, the challenge, looking at resiliency, the challenge is that investing in grid resiliency does not kind of fit your traditional regulatory framework, right? So reliability, we all know how to do that. The utilities know really well about how to plan for it, how to finance it, and kind of make sure that the day-to-day operations are okay for the grid. So the metrics exist, and they are very commonly used by the regulators, so they're very aware, about what everybody's talking about. But when you're talking about resiliency, which is really kind of investing to prepare for and adapt to changing conditions, that could be only happening, once a year or once every few years. How do you value that? And they're definitely not widely accepted metrics. There's a lot of ideas out there, but if you try and say, okay, well, how do I value resiliency? You're not going to find a lot of information out there. So our approach is really to examine the impact of recent hurricanes in North Carolina. We're really going to focus on Florence because that was the one with the biggest impact, and consider kind of 3 scenarios: the current grid, then Duke's proposed grid improvement plan. So if you implement some of the solutions that are in the plan, how would that look? And then a more advanced scenario, if you will, looking into including more distributed resources, whether that's solar storage or additional, natural gas generation or diesel. This is really fuel agnostic too. So, if you implement more DERs, will you have a more resilient grid? What does this look like? So the framework we're using is from Sandia National Lab. It's called the resiliency analysis process, and that's kind of what the graph here is too. So how do you go about this process? By defining your goals and looking at the metrics and characterize what you call threats. Like in North Carolina, you would typically say the hurricane is a threat, but then if you go more in the mountains, maybe you're looking at things like ice storms or extreme rain, flooding, things like that. And kind of go through that process to evaluate the grid, the solutions, and see kind of what the end result is. So this is a map that our students created with some of the data we have so far. We are further than this, but this is the best the best map I could find. So we're going to really focus on New Hanover County, just because it was hit severely during Florence, and they were parts of the county were out of power for a number of days. So, looking at this and looking also at the socioeconomical impact of the storm. So not just the grid itself, but, who was affected most. And how do we make sure that when we are looking at solutions, we take into account all the different things that should be taken into account. So this map is really just a mobility and power outage. So, most of us have a car, but that doesn't mean everybody has a car. So if you look at the colored parts are just kind of households with no vehicle at all. So the lighter is 0 to 2%, going up to 22 to 37% folks that do not have a vehicle. So this here is, if you know Wilmington, it's kind of uptown Wilmington, it's close to the river. So this is a more, this is really a poor part of Wilmington, honestly. So, these folks do not have a car. It had flooded. There was no power. How do you make sure that you create resilience nodes, if you will, where folks that need access to services during these types of events have access to services? So that's one way of looking at. Then, of course, we are, looking at different parts of Wilmington too, where older neighborhoods, for example, a lot of trees, the trees fell down. Maybe undergrounding is the best solution there. And Duke has already, kind of included some of those plans into their grid improvement plan. So that's one project. So this is more, looking at the system level, if you will, of the grid. This, I don't know extremely a lot about it, so I'm going to go over it a little bit quicker. But this is really an industry-sponsored project. The sponsor is called QM Power. So it's really at looking at rapid product development and then commercialization of a product that the QM Power has. So they have what they call the QSync. So it's an innovative AC to AC controller that eliminates the need for AC to DC conversion for motors and motor drives. So the idea is, how do you go from a product that QM had developed? So they have some ideas about a single phase motor drive that uses the QSync technology, and how do you take that concept and then develop it further? So QM presented Epic with some ideas about that single phase motor drive, and then Epic take those ideas and those concepts and develop a three-phase drive topologies that would again try to get that, reduce costs and increase operating efficiency. So that's kind of the idea behind this project. And so this is kind of how we look at it. So it is more of a very short period. So this is completely not what the universities typically do. So we're looking at sprint periods. So 3 months kind of chunks, 3 months. The first period is 3 months. The second period is 4 months. So taking those concepts, Epic is working more on looking at, looking at what exists there. Is there our technology, looking at the benchmarks, establishing a performance criteria, looking at designing the circuit and control model, and then, of course, doing a performance evaluation. And then QM Power, so the company itself, is kind of on the red line, is like, okay, how do we make sure that we work together on, what is being developed. So don't let Epic do whatever Epic wants, but make sure that there's enough input from the company. So in this project, the company and Epic are working very close together to develop this research. QM actually has hired 2 of the PhD students that were working on this project, so they obviously did a very good job. So this is looking at the project kind of broken up between project management, technology development, and IP generation, which is, again, a big thing when working with university research, is what happens to IP. State universities are different than private universities. There's very specific laws that kind of go with IP. So this is also a new kind of concept that we are doing with this company. So by law, all IP that is generated by a public North Carolina university belongs to the university. So obviously, when you have sponsored research that is from industry, that is not a very good idea. So in this case, the university worked with the company, and the IP generated will belong to the university, but there has been an exclusive license agreement with QM Power. So anything that is developed, the IP belongs to the university, but QM Power has the exclusive license for the IP. So this is a new way of doing things. It's typically not done. My contact for this is Jim Gafford. He's the project manager for this specific project, and he's like, that's what we're doing, and it's a good thing to tell people, but maybe it's not a good thing to tell people. So it's one of those things that we take information. Companies come to us and say, well, this is what we want to do, and then we try to figure out, what is the best way to do it. So both the university kind of wins, but also the company wins, obviously. So this is really about, product development research. And then this is the third project that I wanted to talk about. It's called Solutions for Curbside Charging for EV Vehicles, Planned Urban Growth. So the project objective is really, how do you develop, deploy, and test a prototype electric vehicle supply equipment that can be retrofitted in existing streetlights. So we are looking at both the hardware, software, enclosure, and integration in this specific project. This project is funded by DOE, and it is in collaboration with Eaton, Duke Energy, and Central Carolina Council of Governments. Also, the City of Charlotte is part of this project, actually, because we are working with them to deploy a couple of these prototypes in some parts of the city. So looking at this is, that is the main the goal, but how do you need to understand the market for this. Is there a need for these types of charging, this type of charging infrastructure? And then, of course, we need to look at the different challenges at retrofitting a street pole to be able to accept a level 2 charger in this case. The reason why we're looking at this is because 90% of charging, if you own an electric vehicle, you will probably charge it at home. Some of us are lucky enough that the places they work have charging stations, but that is obviously not the case for everybody. So now, unless you have your own garage, you probably are not have an EV. How can you do this curbside that's challenging both for cost, if you need to rip up pavements and tap into the lines, but also access, where can you really put them? And then, of course, there's a limited understanding of the ability to integrate these into existing streetlight infrastructure. It's never really done, so how does that really work? So for this, the kind of the enabling technology is this new circuit breaker that Eaton created. This, I think, is now out into the world, if you will. When we started working on this, they were still developing this breaker. So, and it's going to come out in 2 breakers. So it's going to be your simple breaker, but also with that level 2 EVSE feature to be able to use it for charging. So it's solid state disconnect, it's Wi-Fi accessible, and it provides full monitoring and control of the charging. And, if you're looking at implementing some of these things to streetlight, then of course you need to be working the utility because metering accuracy will be important, right? So this is kind of this project. That is our dean here. We have one of the prototypes here on the university, so he is actually using it to charge his car, and the car didn't explode, so that was a very good first test. So up to date, they have developed and deployed what we call the alpha prototype. So that's really what you can see there on the pole. They're looking to make them obviously much prettier than that. And it used to be a much larger box too. So that is already a much smaller box than it was initially. So they've developed an alpha version. Our students have worked with the software to have, a mobile app interface, if you will. And then what we're still going to be doing, and I'm not sure how far they are now with this, because they were going to develop and test this also at the Mount Holly site at Duke Energy. And they were going to look at different locations, like I mentioned, with the city of Charlotte to put some in the city and just have kind of the public start using them. Another big issue with this is to see, what kind of policy is there and how permitting can be an issue when looking at deploying these types of things. I think that's my last slide. I have talked a lot. So this is a very, this is a general overview of what EPIC does. And again, if you have specific questions, if you want to share, and if you want me to share more information, contacts, things like that, please let me know, because we are happy to do that.
Christina, we have a few more minutes before 10:30. Let's see if anyone has any questions, and I've got a few follow-ups for you. How about anybody out there that has been able to digest all of this, which was just huge?
Yeah, sorry about that.
No, it was great.
Yeah, it was absolutely wonderful. And Christina, this is Dawn Hill. I'm with the city of Charlotte, and I'm glad that we're working with you guys, especially on those smart vehicles. I just have a question of one of the programs that reports up to me is the Mayor's Youth Employment Program. Mm-hmm. And it's a traditional internship program where we provide opportunities for students to intern over the summer and gain more experience and career development opportunities as well. I would love to circle back with you and talk about how we might be able to take our, some of our engineering and energy students and plug them into what you're doing out on that campus, because this is absolutely mind-blowing.
Yes, please follow up with me. I'll be happy to talk about that. We're all about workforce development.
Wonderful. Glad to hear that. Thank you so much. It was a great presentation.
Thank you.
So Christina, just to give some perspective, we know that there's a number of universities that maintain energy research programs in the Carolinas. You have Clemson and NC State, which are part of the CAPER program. And then you have University of South Carolina. You have Duke University, Wake Forest focuses a little more on the softer side, the environmental side, App State, NCA&T. So I'm interested in just how far UNC Charlotte's reach is. Give us an idea as to how many companies, say over the course of a few years, you would estimate are engaged in industry-related research, and how far away are these companies? Are they just primarily clustered around Charlotte, or is it regional or national?
Yeah. Well, it's definitely national. I'll start with the easy side of things. So we have, we've done projects with companies like, out in California, and utilities out there, or a lot of the projects we work on are collaborative projects with other parts of the country. So another project I didn't mention that we've been working on now is with, again, it's a DOE funded, NREL administrated project that is about resiliency in remote and island communities. So we're working with that with ECU actually, and the Coastal Institute at ECU. But that is part of a conglomerate, if you will, of different parts, different centers around the country. So we are working with people from Alaska. We're talking with people in Maine. We're here in, us in the North Carolina side of things, Hawaii. So I'd say, in a typical year, we probably talk with people all around the U.S. and work with people all around the U.S. I'd say the majority of the companies we work with are around the Carolinas, just because there are so many of them around the Carolinas. I think there's not been a lot of need to continue, going further out. But we definitely touch, around the U.S. And thinking about how many companies we work with throughout a year, gosh, I'm not sure I have an accurate number, but I'd say at least 50 or 60. It just depends on, and some project we may be working with a company at the beginning of the project, and then, we've kind of gotten, the relationship, that's where it needed to be, and then we're moving towards something else, and maybe a different company is involved, at that point. So one project may have by itself, 10 companies that are working on it. Another project we just got in from DOE, from the Solar Energy Office, which is going to be a multi-million project that has a number of universities, a number of companies, so already by one project you have 30 companies working together with different universities. So
Christina,
is the answer.
a lot, yeah. So how about anybody else? I've got another question for Christina, but how about anybody else has a question about EPIC and the research program? All right, you get another question from me. So we saw a lot of research labs. Is all of the research in those labs a result of businesses approaching EPIC for research, or what portion is pure research by the faculty there or the students there?
Yeah, so that is a good question. I think I'd say, especially for EPIC specifically, so I'm not talking about the College of Engineering, for example, because that is a lot more faculty focused, if you will. But EPIC was designed to be collaborative. So I'd say from our project, probably about half are purely the ideas of faculty, if you will. So, that's how the research started. But later on, a lot of those also will start include industry. Because the whole point is not to just make a thing that nobody is going to use, even though if it's the best thing ever, right? If you can't get into the market, then it doesn't mean anything. So even those ideas that were developed by faculty at some point will start including, if there's any merit to it, that it's something that can be, commercialized, or if it's a concept, that it can really be developed and deployed into the field, then companies will be approached at a later level to come and be part of it. And then I'd say about half of them are really either companies approaching us or EPIC approaching companies for interdisciplinary projects also.
Do you have any idea of the results of research? So just a ballpark, what portion of this research winds up going into application or forms the basis for a new company?
I don't have an actual answer for that, but what I can tell you is that we do a lot more applied research so our research is not fundamental. So it's typically already beyond it's a solution to a problem, kind of the work we're doing. It's not like let's come up with a completely new concept, like, you get in the more fundamental types of research. So, I mean, I know we've had a number of companies come out of EPIC while I was here. So probably, I don't know, 7 or 8, and I've been here since 2006. So let's late 6. So say 4 or 5 years. So an average of 1 to 2 a year, maybe. But a lot of them are either student driven, or a lot of them are actually faculty driven. So it's faculty that has been working on a project, for example, with DOE, and they have developed some kind of device. And then once DOE has stopped the funding and the IP has all been sorted out, that may be, become a company or some kind of spin-off, if you will. But I don't have an exact number for you.
But a lot of it's applied though. So it's a lot of it's
Yeah,
intended
it's
to solve
typically,
problems.
we're typically further down the road, if you will. It's more like, okay, this is the problem. These are the different solutions that are already exist. What is a better solution? Or there's no solutions. Let's think about what would make sense to work on.
So we're about out of time. Anyone have a final question for Christina? Going once. Going twice. Christina, thank you very much. That was an amazing presentation. Lots of hand claps, lots of thumbs up. Well done.
Thank you.
Yeah.
Well, I hope you enjoy the rest of the day. And I did this back in 2017. It was a great experience. So I'm glad to see full class again.
Yeah, you're getting lots of good signs here on the video. So, and yes, Christina's an alumni, and when you all graduate, you'll be an alumni with her. So
Exactly. We can go have drinks together once we can go out again.
once we go out again, that's exactly right. Jeffrey is the R&D program manager for low carbon resources at the Electric Power Research Institute. He joined EPRI in 2014 after 5 years with Duke Energy. He leads the joint EPRI GTI Low Carbon Resource Initiative and manages EPRI's research portfolio on production, storage, delivery, and use of low carbon chemical energy carriers. Holds an MBA from Wake, chemical engineering degree from NC State. Jeffrey, the platform is yours, and we're good right up until noon. So you're good until high noon. Jess Buchanan and I will be in the background. If you have any technical problems with the presentation, let us know. We can step in and get those sorted out for you.
Okay, great. And I invite all participants to interact either via chat or I'm assuming you can all unmute yourselves and talk to me. That would be great as well. I'd love to have a conversation as we go forward. So thanks for the time to be here. I'm really excited to talk about this topic because it's very much relevant to the world of energy today and a critical part of our future. And to give you a little background behind the motivation of the Low Carbon Resources Initiative and many of the efforts that are underway at EPRI, we have to first look at where the trajectory puts us for CO2 emissions around key climate goals, those specifically established by the Paris Agreement. And when we look at CO2 emissions, it's no surprise that there's not one country or one region of the world that's likely to be a player onto its own, and that collaboration in the highest sense is critical to reaching many of these objectives, which have been agreed to by countries, by regions, by cities, by companies, the like. So as we think back to the Paris Agreement, recall that the initial standards of the goal are established in a 2015 timeframe. So looking at emissions reductions from a 2005-2015 timeframe, and then projecting out towards ultimately a 2 degrees Celsius limitation on warming. And then backing out what the projected scientific measurements and analysis would conclude would be a limitation on CO2 emissions across all aspects of our economy. And so when we think about here on the right, then where we stand relative to this 2 degrees limit here in this inner circle is that if we continued as the folks at the IPCC suggest at a business as usual case, then we would likely exceed in terms of emissions and then potentially exceed that 2 degrees Celsius warming. And so business as usual clearly is not the path forward. And it's really the subject to ESG goals and targets. It's the US having joined back again the Paris Agreement, other countries such as China setting net zero emissions targets, Japan following suit, et cetera. There is quite a momentum happening. And then now on the corporate level, we're seeing it from utilities, gas and electric. We're seeing it from OEMs, such as the GEs of the world, saying that they're no longer participating in building new coal units, seeing it from the EPC firms saying the same thing. We're also seeing it, though, from investor communities. We're seeing it from BlackRock and other large organizations who have a very strong influence on markets and positions of various organizations. And so largely buying into the fact that we've got to do something about this global challenge, and we've got to do something sooner than later, but we have to do it in a way that recognizes the role of markets, the role of technology, the role of organizations and companies worldwide in trying to achieve these targets. And so when we at EPRI have looked at and begin to hypothesize various pathways forward to achieve these decarbonization targets, we look obviously at the role of electricity. So starting with the way electricity is produced, moving and transitioning towards a lower carbon future. We're seeing that certainly in the US, where emissions reductions are on a steep decline, but largely due to changing from coal to natural gas and then the increase in renewables. And I'll show you where we're projecting that trajectory to go based on the path and the acceleration that we anticipate having over the next few years. But it's also important to remember that something like 3/4 of the world's energy today, this is a global number, relies on fossil fuels. And we believe that if we're to achieve an affordable, reliable, resilient, low carbon future that has all of the characteristics of equity, resiliency built in on top of it, that other technologies, such as those using carbon capture, utilization, and storage, would also likely need to be in the picture. And that many of these technologies, specifically because they are at commercial scale, and then looking towards adoption in areas where it makes sense. Specifically, where could we put CO2 storage? Where would it make sense to do so safely and economically, and in support of other transitions to decarbonize the electricity grid? And then, of course, dealing with batteries, distributed energy resources, efficiency, and then ultimately some components of electrification. So we know that if we have clean energy, clean electricity being produced, and then utilizing that electricity to support various aspects of the economy, there's a clear role for electrification to serve in that decarbonization pathway. And as I'll show you just a few slides, though likely not to be enough. But then it gets challenging because we, in our projections and in many other projections, we could probably get, in the US perspective, 80 to 90% of the way with low carbon generation without it significantly increasing the price of electricity or causing interruptions or going outside of where we anticipate technologies and deployment of technologies outpacing reality and capabilities. And so we have to consider then the next phase, what we consider to be the next phase of decarbonization. So it's beyond the path that we're already on, which is retiring coal assets, increasing natural gas utilization, increasing renewables, batteries, et cetera, deploying CCS. There's also a role then to figure out the last, as I said, 10 to 20% of decarbonization. But then likewise, if we think about the rest of the energy economy, where 40 to 60% of final energy use likely could not be electrified, how will those parts of the economy reach the decarbonization targets that are set forth, so that successfully we can say that we've achieved those CO2 emission reductions and keep warming below the 2 degrees target. And so these areas which are shown here are highly evaluated for the potential for other non-electrified technologies to be deployed, because they represent either extremely high energy demand, high loads, high temperatures, availability is needed on a short-term basis. It could be that distributing these resources, such as those in buildings, doesn't equate to efficiency, or cost would be astronomical to the consumer. And so taking into the economics and the market drivers and policy all have to be considered when we look for pathways to decarbonization. So where do we go for that last 10 to 20%, and what does the rest of the energy for the electric sector, and what does the rest of the energy economy do to affordably transition to a low carbon future? And this culmination of ideas and concepts, something EPRI calls Project 2X to 2050, it really highlights that there is a significant effort around these 4 pillars. But the 4th one is the one which I'll speak to you about today, and is the subject of the Low Carbon Resources Initiative. So what we're saying is that energy efficiency must continue. We've been on a great trajectory to improve the amount of energy that's being utilized from an efficiency standpoint, that we must continue creating and generating clean electricity through wind and solar, batteries, but also through nuclear. We're seeing license extensions through the 2nd round. We're hearing, as of yesterday, I read there are considerations for a 3rd round, which would give licenses up to 100 years for existing assets. And then, of course, looking at the role of potential new reactors, designs, et cetera. All of that will continue on. But then when we consider further deep carbon reductions, then the role that we foresee electrification playing, there is still a significant portion of the economy and the electricity sector which cannot be served by these first 3 pillars. So these low carbon resources, which is the subject of my talk today. So we consider these to be either energy carriers, alternative energy carriers, or fuels, depending on how they're used. And really, it's how can we make and deploy these fuels, such as hydrogen, ammonia, synthetic fuels, and biofuels, in a way, in a low carbon manner, but also affordable, and it still maintains the same energy perspectives that consumers demand, and apply that to other parts of the energy economy. Well, it's no surprise that there's a potential role for electrification. We call it indirect electrification, because what we're saying is that electricity is a feedstock, if you will, to the conversion process to create a fuel. So here specifically could be converting water into pure hydrogen through electrolysis, and then driving that through clean, low carbon electricity. Others call it power to gas or power to X. But then there's also this aspect of existing technologies, biomass conversion processes, steam methane reforming, which makes up the majority of today's hydrogen production worldwide, but deploying low carbon assets and technologies such as CO2 capture and storage. And so thinking about how then these energy systems become even more integrated to serve the purpose of decarbonizing the entire energy economy. Because while the electricity sector in its own can be evaluating pathways to decarbonization, again, it's clear that there is potential role in that last 10 to 20% of decarbonization for other alternatives. And so this arrow pointing back towards the electricity sector is also critical, because as we will show you, some of our analysis suggests that there could be a role for hydrogen specifically in energy storage and energy utilization to help achieve emissions reductions across electricity production. So then if we take a step back and we think about these 2 perspectives which are emerging. One here on the left is that the utilities themselves in the electricity and gas space are making efforts to significantly reduce their CO2 emissions. And they're doing that with a number of options and pathways. So looking, as I mentioned, renewables, nuclear, batteries, efficiency standards, methane reduction from pipe leaks, increasing efficiency from a natural gas perspective, but then also considering the role of CCS, hydrogen, and even carbon negative approaches. And then thinking about the rest of the energy economy, how will they transition? And there's a great amount of effort being focused on the transition to this low carbon future that establishes a supply chain and a value chain of low carbon fuels that is sustainable throughout the future going forward, and also reliable and cost effective. So I'm going to break down now more of these aspects for decarbonizing the electricity sector, because it plays actually a substantial role in the impacts and the opportunity to decarbonize the rest of the energy economy. And as I said, feel free to pop anything into the chat or interrupt, ask questions, provide your thoughts, comments. I don't have to talk consecutively here. So the first thing it's important to address when it comes to decarbonization is defining what we mean. And you've likely heard some of these phrases and words, and as you can imagine, they mean different things depending on who's saying them and what they mean. So we've run 3 primary scenarios, one on net zero, one on carbon free, and one on 100% renewables. And we'll tell you why our approach is really in that first area of a net zero emissions economy. So net zero, as it sounds, any amount of emissions that go up into the air are offset by removing emissions from the atmosphere or directly from the point source before it reaches the atmosphere, and then stored or utilized in the case of a circular economy to essentially establish a net zero emissions profile. In this case, as you can see, all relevant electricity generation options are kept on the table. In the carbon-free scenario, we've essentially taken out all options that result in the emission of carbon, whether that carbon were to be captured or not. And so in some areas of the world, there are many regions that are on this pathway. We're seeing this in France specifically, where they have been promoting more of a nuclear and renewables with some applications of batteries and potentially hydrogen in support. But in other parts of the world, other economies, different drivers to make decisions on if and how carbon-free makes sense. But essentially here, there's no fossil fuels being used, there's no emissions. And again, this is just for the electricity sector. This isn't for the entire economy, not yet at least. And then the last case is where we're producing electricity only from renewables. So there's no nuclear, there's no fossil energy, it's only primarily wind, solar, hydro assets. And then we'll use these definitions to talk through the implications from a cost perspective. EPRI maintains a U.S. energy economy model. It's called REGEN, R-E-G-E-N. That is a tool that we use to help project out the role of various systems and technologies across the electric sector. It's something we're expanding as we launch into the Low Carbon Resources Initiative to account for hydrogen and other low carbon fuels. So let me walk you through these very busy bar graphs because they tell a very interesting story. So here on the left, we're looking at the capacity mix for various zero emission targets. So we've got net zero, carbon free, 100% renewables, and we're looking at it from a 2035 timeframe. So what would it take to hit these definitions in the electric sector by 2035? Chosen, of course, in part by the recent Biden administration perspectives on working towards these various targets for the electric sector by the same date. So a few reference cases to consider. 2020, this is based on the U.S. Energy Information Administration, and then the projection out to 2035 is their projection as well. So it essentially says that any existing or finalized planned state level policies go into effect. So we think about specifically that I'm aware of New York and California, maybe a few others have some stage gate approaches to hitting their 2040 and 2045 targets, but there's no federal targets applied in either of the reference cases. Obviously, this is last year pre-COVID, and then projections, and then the 2035 projection. So what you see is that in the net zero case, we're projecting out the lowest amount of capacity, so the lowest amount of deployment of technology from a capacity perspective. And then you can see that there's obviously gas involved, and then the role of CCUS applications as this darker color orange plays into achieving net zero. So what's interesting here is that it shows us that not all of the gas assets, so natural gas combined cycle combustion turbines, is all set through CCUS because we're projecting a role of bioenergy with CCUS, which achieves a net negative emission reduction. So it essentially says from a capacity perspective, we wouldn't necessarily need carbon capture and storage on all natural gas electricity assets, that we could instead prioritize CCS in areas where it's economical, where there's storage, where there's adequate capacity factor for the gas asset, et cetera, to balance out the perspective of achieving a net zero emission target. As we move into carbon free, we're essentially removing the gas asset. Now, gas actually shows from a capacity perspective. If you sneak a peek over here to the carbon free area, it's not actually showing in the generation mix, but it's here because we recognize to some degree there is amount of resiliency and reliability that is afforded by having natural gas capacity available. Certainly the events from about a month ago now in the middle of the country showed us that there's likely to play a role in every technology going forward. So here's where we start to see hydrogen appear. We start to see a little bit more battery storage appear, but then largely we're seeing more and more wind and solar and playing a role from a renewable space. Then the last in 100% renewables, the highest amount of capacity projected, largely because the capacity factors of these assets, but also because as you deploy more and more of these assets, you're deploying them in areas that aren't as efficient or aren't providing the highest level of output. And so you need more of those assets to maintain critical assets of capacity in support of the overall target, which is the renewables piece. So very similar story over here on the generation mix. Note there's conversion of units, so we're in terawatt hours here. And then largely you see, okay, well, here's the role of gas as of 2020 and coal and others. And then if we're on the trajectory of 2035, again, kind of business as usual, projected reference case, versus the role of these technologies where we see nuclear providing the largest contribution in generation in a carbon-free environment. But obviously, if we're at 100% renewables and there's no nuclear, all that primarily offset by wind and solar. And then even still, we see still not an insignificant amount of hydrogen being used as part of the, so this would be hydrogen dedicated to gas turbines, but a lot of battery storage, so shorter term 4 to 8 hour battery utilization in the generation load mix. So then the question from an economics perspective is, okay, if these are technically relevant and directionally accurate, what's it going to cost? And so when we evaluate these different scenarios, we look at putting all of these are all dollars in 2015. So there's $2015 per megawatt hours. We're not adjusted for inflation. Everything's referenced back to 2015. If we continue on the reference case, you can see largely maintaining around $60 per megawatt hour. But then by keeping as many technologies options on the table, having the lowest cost, the lowest average cost in the US for electricity, and seeing higher cost as we restrict those technology options, where achieving the target of 100% renewables by 2035 would result in the highest economic cost of electricity generation. And we see that there's a decrease because over time, the rush to put these technologies in, to keep up with demand, and to essentially force the market to go in that direction suggests that we would see a peak in prices and then a leveling or a drop down and eventual leveling as new assets are rotated in and optimization occurs as we're talking significant amounts of new generation being applied to the grid. So key takeaway based on our economic analysis, net zero gives us still a target that appears to be achievable in the sense of the technologies that exist today, not all of them fully commercialized and proven out, but based on the cost projections of those technologies, the net zero case gives us the lowest economic option, lowest cost, best economic option to achieve zero emissions by 2050 in the electricity sector. So let me pause there. I'm happy to take any questions.
So I have a question. One thing I was wondering is nuclear, could you expand a little bit on why, and I apologize for not having my camera on, but I've been having some connection issues, so I turn it off. But so could you just expand a little bit on why nuclear was not included in the renewables? I know a lot of people, because nuclear, we have enough uranium and thorium to do nuclear for, hundreds of thousands of years. So I know a lot of people consider that renewable, so I didn't know why the cut was made one way or the other.
Yeah, it's a good question. It's mainly because when we analyze the definitions that are used, particularly in the policy space, nuclear is not normally included in our 100% renewables. So we've tried to provide context around the definition. We don't certainly own or suggest that we own these definitions, but when we consider the U.S. perspectives on nuclear and the conversations that are being had in various regions, that there's question that nuclear would need to be a part of the energy mix. And so we wanted to show the role of nuclear in various targets. And essentially, this analysis was a bit contrived to try to target more of the boundary conditions of decarbonization. So it's definitely not an answer. It's just to say, if this were the definition to be followed, these are the results that would come about from that.
Gotcha. Thank you. That makes perfect sense.
Yeah, EPRI has a very robust nuclear program. I'm sure many of you probably know this. It's our largest funded area across the Institute, Global Perspectives. And so we're very keen to continue the work in nuclear. As a whole, EPRI believes that nuclear, extending licenses, developing new technologies, using nuclear beyond electricity for other aspects, including hydrogen production, but also in desalination, medical isotope production, et cetera. There's a larger role for nuclear to play, and we have a lot of activity to continue emphasizing the role of nuclear going forward.
Thank you very much.
Okay, so what's interesting then is if this is the 2035 number, and a thought exercise that followed was if we took these same definitions but applied a 2050 timeframe and said instead of hitting these target definitions by 2035, what would happen if we hit them by 2050? And so as you can see, largely in every case, the cost would be projected lower. So again, with more time, you have you're not rushing into the market, you're not pursuing economies of scale too quickly, you're taking advantage of learning curves, of deployment of assets and people and just timing. And so projecting out lower cost across the board for all of the scenarios. And in the case of net zero, then largely still having the same impact overall. So timing is of critical essence to this. Now, timing can go the other way because, as I mentioned in the first slide, we know that we have to accelerate the pace of change for decarbonization. So there very much is a balance to the role of these technologies and the timing, and that's really where the LCRI will be digging in, as I'll explain to you more. I'll skip through some of these. So then the economy-wide approach. So at a high level, on the left, what we're seeing is this reference case, the business as usual, instead of projecting out to 2035, now we're showing 2050. And again, this is the US perspective. And then if we look back to the historical changes, we're projecting that across the entire economy in the US, we would achieve 50% reductions below the 2005 baseline in 2050, primarily based on the continued role of natural gas, of renewables and electrification, efficiency, et cetera. So clearly a long ways off from the zero target in 2050. If we were to model the electric sector going to zero emissions by 2035, and I gave you 3 examples of how to do that, we'll assume it's the net zero case because it actually has significant implications on the economy-wide approach. So if we assume a net zero approach where we've hit zero in the electric sector, what we can see is that compared to the reference case, we're now 70% below the emissions reduction from 2005. And how we got there was the portion relevant to the electric sector. So the same blue area under the curve here, and the economy, obviously electricity is one of the largest emitters of CO2. So getting those reductions out of the way shows the impacts in the entire economy. But then what's also interesting is that in taking the net zero case, we incentivize a transition in other areas to pursue further electrification, further meaning that it's more is picked up beyond what is in the reference case. So there is an amount of electrification here. Actually, I meant to look up the number because I was asked just the other day. I can't recall exactly what that number is, but picking up additional. Now, the way to study that, because the model doesn't force any end-use perspectives. It doesn't say that any area, that each of us will have to own at least one EV or will have to go to heat pumps or whatever. It says based on the cost of technology and based on various factors, economic factors of consumer choice, modeled by applying $1 per ton of CO2 with an escalation rate, we would see that it's beneficial for consumers to switch to electrification, and this is the portion that we would suspect in doing so. I seem to recall that the Biden administration recently put out a target of about $51 per ton. In Europe, we're seeing this nearly or more than double in some cases. So depending on where you're at in the world, these values are all over the map. But they're also important because in many parts, especially the hard to decarbonize, which is essentially this blank space here, we could go 10, 20 times higher in the ton per CO2, still wouldn't move it down because, again, not every part of the energy economy has the same economic drivers from a CO2 perspective. So when we look at this full economic arena, this is the role we see for potentially for low carbon fuels. And this is the subject of the Low Carbon Resources Initiative, that there are a number of pathways to achieve decarbonization across the energy economy, across the electricity sector. But when we project out how to get there by 2050 in a net zero environment, it seems that there is likely to be a significant area, significant parts of our economy, and even parts of the electric sector in some cases, depending on that definition, that will rely on an alternative fuel, alternative energy carrier. And that's really the motivation behind our new initiative. And you can find a lot of details. This is publicly available. So when you get these slides, you can link directly to the EPRI website and download this for free. You may be required to create a login, but it's a fairly straightforward process. So as we think even deeper into this low carbon energy transition, we talked a little bit about technology so far, certainly a lot more material we could cover. We talked a little bit about the timing and the role, not only from an emissions perspective, but how these technologies get rolled out. These were US perspectives. So we have as I mentioned, our tool is very specifically modeling the US, but we are working on capabilities and actually have the capabilities to model other regions of the world. You've probably seen these, or you can find them from the IEA or other organizations who study these on a country by country perspective. And then of course, cost. And so if we think about then, as one example, a market perspective and a value chain perspective to a low carbon fuel such as hydrogen, because hydrogen is getting a lot of attention. It's followed numerous cycles over the many decades, and now it seems we've reached maybe a pinnacle and an interest, and hopefully now a lot of investment, it seems, to continue pushing the deployment and then the utilization to achieve that low carbon future. So here, if we just assume for perspectives, just market perspective, according to the IEA in 2019, 70 million metric tons of hydrogen was produced in that year. Of that amount, about 70% of it came from natural gas, and there was no CCS applied. And then about 28% came from coal gasification. Less than 2% came from electrolysis. And primarily that was not the electrolysis we talk about in the energy space today. It's byproduct from chloralkali and other processes. But let's just say we took that 28% and tomorrow converted it over to just using electricity and assumed, maybe not tomorrow, maybe 2035, the electricity grid is net zero emission. We decarbonize the grid and then create water so it's blue or it's green or it's white or whatever color we decide to call it then. That would result in essentially the amount of electricity used by the country of India today. It's a significant amount of energy. So splitting water into hydrogen, while it sounds fairly direct, has implications across multiple areas. Not only the electricity, that's a lot of energy to use, but then also you've got to store, you've got to deliver, you have to have market demands and consumers who value and know how to use hydrogen, et cetera. And so then the obvious question is, well, what about the trade-offs? And so could we not just tack on CCS to natural gas reforming and then understand how that shifts the global market for hydrogen and other low carbon fuels? And the answer is absolutely. And we started to do some of that work. So the LCRI specifically, again, if we're going to be really focused on getting those 2050 targets in place, we have to look at the entire energy economy, because hopefully you've seen now the motivation suggests that just the electricity sector alone leaves still a sizable gap. And so we're focused on how hydrogen, but also ammonia, synthetic fuels, and biofuels, how they become incorporated into various value chains. So from a consumer perspective, but also from a supplier and middle market perspective, in order to drive these decarbonization targets and hit them by 2050, as is the overall goal. And then specifically, what we're looking at in our initiative is how to do this in a way from a perspective that a number of these technologies exist, but they're not at scale. So I showed you less than 2% of hydrogen produced by electrolysis. There's quite a ways to go in the world if we're going to make up for even just the global consumption of hydrogen today. Some project that will be 4 times the amount it is by 2035, some much higher, and then exponentially to 2050. So there's a long way to go to get the market primed. But it's more than just supply. it's about the end users, the conversion. So here we're seeing, you know, how do we convert fossil fuel utilization to ammonia or hydrogen combustion and heating in transportation and electric power generation in some cases. And then where's it going to come from? How are we producing it? Can we do it in a low carbon way? Can we do it in a way that's affordable, reliable, resilient? And then how are we going to move it and store it and get it where it needs to go, and all of that safely and without having any negative environmental aspects to it? And so this is the focus of our new initiative, which we've launched with GTI. And then, as you can imagine, there's all kinds of trade-offs, especially on the end user side. I showed just one on hydrogen production. But we think about the way the world moves and uses energy today, there's a lot of nuances to these technologies. So it's important to understand the role of the next set of CO2 emission areas as the electric sector continues to decarbonize. So transportation being the leading one now, but then buildings and other industry applications following closely behind. And what's interesting, though, is that as we move forward, we believe, and many others agree, that integrating these energy systems, it has to be a focus in order to achieve affordability, reliability, and doing this in a timely manner. One sector cannot be successful in deploying hydrogen or another low carbon fuel on its own. It might be successful in the demonstration, it may be successful in setting up its own supply chain, but in the end, if our goal is to achieve economy-wide decarbonization, it's going to take a lot of moving parts working together to make this transition happen in an effective way. So a little bit of background, but then what's really interesting about the complexity here is it's not getting any simpler. So I show this graph only to say our modeling team is using it. This is kind of, we call it a spaghetti chart, but it outlines the inputs, outputs, relationships to a lot of energy systems that our energy economy tool uses, which displays the nice, the data that we turn into nice figures, but essentially shows clearly that there is a role for many what we consider to be primary energy sources, and that we are focused specifically in this LCRI how these other low carbon fuels and energy carriers, and then in addition, the trade-offs with CO2 capture and storage play in achieving a net zero future across various end-use applications. So it's unfortunately not getting any easier, but there are ways to avoid this chicken and egg. Well, if we need the hydrogen, but it's not cost effective, we can't change our equipment to modify it, but we can't make it more cost effective if we can't produce it at higher quantities. So we have to wait for the market to demand it. So there's all of these gives and takes that we're studying and incorporating in our analysis, along with what technologies need to be developed to support it. So I'll skip over some of the energy modeling stuff and maybe just dive into electrolysis, but I'll pause here and take any questions.
How about questions for, how about questions for Jeffrey?
Okay.
Okay, everybody's following.
I guess so, or they're asleep, whichever one. So we're working towards producing, on April 16th, we'll have a publicly available document, which is the research vision behind our initiative. And you'll see there are 8 areas of our initiative which define our research priorities. One of those is around electrolysis. I'll take the remaining time we have to talk a little bit about our approach to this research vision and plan, but you'll have access because it's publicly available, and we can make sure that the leads here, if they're inclined to share it and there's interest to follow up, or you can reach out to me directly, and I'm happy to pass it along. You'll be able to look through this in more detail. So I mentioned value chain. What does that mean practically? And what does that mean from the context of a research institute? Because we aren't prescribing or advocating for specific market conditions or technologies. Rather, we're exploring through R&D the role of technologies and systems coming together in ways that have yet to be done on really any substantial scale. So when we look at electrolysis, obviously it exists to produce hydrogen. That hydrogen goes somewhere, it's used for something, and there are many different technologies that could be deployed to make that hydrogen. So we're looking at the technology development, we're looking at what it means to have that system on the ground running. There's what we call balance of plant systems. So auxiliary, water treatment, desalination, cooling, power quality and controls. There's a bunch of stuff that has to go into supporting the hydrogen production process. But then also looking at how these systems perform and the conditions that help them perform optimally. Because there's a lot of conversation now about so-called green hydrogen, where essentially the energy supply, electricity supply, is from renewables, specifically because of the color coordination of green, that they don't lump in nuclear. That's another color, maybe pink, I suppose. Anyway, but in a sense, what does that mean then to operate? And I'll show you some examples. But then, of course, no system can go in, no industrial process can go in without considering the environmental health and safety aspects. And then these systems are very complex, and there's a number of manufacturing materials aspects that go into it as well. So that's your system. You're a company and you say, I want to make hydrogen and I want to make it from electrolysis. What do I need to know? Well, you want to know what technology, is out there, what purpose that it serves, how it works, how to put it in the ground, how to run it successfully and safely for 20, 30, 40, 50 years, et cetera. But then you've got to figure out, well, how does it integrate with my energy supply? Because now we're talking about complexity. We're talking about as we shift to more renewables on the grid and intermittency and curtailment, there's all these challenges with pricing and building into the system. There's reliability. It could be tied directly to a nuclear facility providing steam in the solid oxide case, whatever it may be. It's important that we understand the value components upstream of that electrolysis system, and then of course downstream as well, because you're making that hydrogen, but how are you storing it? Where does it go? Who's using it? What are the purity requirements? What are the considerations you have if you're going to convert it to a synthetic fuel or convert it to ammonia? You can't just look at the system and the technology itself. It really needs to be a packaged evaluation. So our R&D touches all of these areas. I mentioned this about where hydrogen comes from today, and then I'll give you a little bit of sense of some of the economics. This type of information feeds into the energy economy model. So this is how we know to project out the various roles of technologies. So if we look at steam methane reforming, and in this case we've added CCS, and the capture rate is 90%. And we've simulated this under $3 per MMBTU and electricity for the electrolysis cases at 5 cents a kilowatt hour. The US DOE, for reference, has put a $2 per kilogram target on the production of hydrogen from electrolysis, largely based on their evaluations of the market and the ability to shift to electrolytic produced hydrogen. So we see that with steam methane reforming, primarily natural gas is a high cost, but there's also a lot of costs from fixed O&M. So here's our key up here in capital. But then when we shift over to electricity, the majority, a significant amount of the cost to produce hydrogen is driven by the price of electricity. So here again, integrated energy system becomes a very strong mean and driver. What can we do to drive these costs down? What are the factors that influence the operation and design of these systems? How will the energy economy come to value hydrogen production in this way? So if we look at 2020 versus 2030, these are various analyses from EPRI, from NREL, from IEA, and others that suggest where we are today in these technologies, we'll see significant improvements in cost, mainly because of economies of scale, because we're just not quite at the level of production that these technologies have reached their highest efficiency, and so likely to see reduction. So that's really the only difference between 2020 and 2030 is economies of scale. So then we're going to play with the inputs, and we're going to say, well, what happens when we increase the natural gas price, because we would anticipate that to go up here for steam methane reforming, and reduce the price of electricity? And we would do that for a number of reasons. But the answer, the suggestion, is that, of course, steam methane reforming would produce higher cost hydrogen, but still under the target in 2020. So at today's prices, we could see that we get fairly close to that production target. Now, again, this is just production. This is not storage and delivery to the customer or what the consumer pays. You've got to tack all that on top of it. So obviously, getting further down the line is better. But here, likely a role of electricity to support if this is feasible. Well, where does this become feasible? We hear it a lot around using curtailed wind or solar, but unfortunately, it's not that straightforward. So if we look at cost sensitivities, the first one being capital cost. So here we have on all of our y-axes the dollar per kilogram cost, production cost of hydrogen. And we can see as we reduce the capital cost, we can reduce the cost of hydrogen production, but it's fairly marginal, very shallow slope here. Electricity price, steeper slope. Obviously, the lower the price, the lower the hydrogen, fairly straightforward. But capacity factor, even steeper, stronger relationship in the lower capacity factor. So capacity factor is the amount of hours this electrolyzer runs over an 87, 60 hours per year value. So the fact that these technologies don't run 100% of the time, they have maintenance cycles, they have upset issues, they have just demand is low, there's not needed, they're not operating. That impacts the total cost of hydrogen production. So to give you an example that tie it back to electricity, the average capacity factor for wind assets, wind electricity generation in the US last year, or 2019 rather, was about 44%. So that means on average, on monthly average, the wind turbines in the country ran 44% of the time every month. Now, we'll just take that number for what it is, even though it's really not a good indication. That puts us right in the elbow of this curve, which is really not ideal, because what we're saying is that depending on where and how curtailment happened, we could be on either side of that capacity factor number. And if we weren't on the right side, we wouldn't be achieving the best economics of production. And so when we study the role of renewables and providing energy, indirect electrification, power to gas, we have to understand the trade-offs and the sensitivities of all the rest of the energy economy coming together to really understand the role that they play in reducing carbon. Because remember, if 40 to 60% of the energy economy, the non-electric portion, relies on something like hydrogen, and they're dealing with significant price swings that aren't economical, it's going to be hard to justify this transition. And so understanding these trade-offs around technologies become critical to the evaluation. One way to help with all of those three scenarios is looking at technology development. And so here listed the four primary technology types in the electrolysis space. Alkaline, which has been operating for about 100 years, more than 100 years, very successful commercially, scaling up very quickly with worldwide demand increasing, but the least flexible of all of the options. Doesn't like to have low capacity factors, doesn't like to operate in transient states, wants to be held very steady state constant, but it's the lowest cost option today. So what does it look like to deploy these technologies across the economy? What is the impact of those? And then others that provide perhaps lower cost or varying degrees of reliability and flexibility. Where can we see these technologies become more commercially deployed? we're working on defining these roadmaps within the LCRI and studying those. So again, it's looking at the system, looking at the specific technology, but also looking at how it's integrated, how it's designed, and then what purpose it serves downstream to really know if and when these technologies could become deployed and what it would take to get there in a decarbonized fashion. Certainly, we're seeing a lot of investment in Europe. Just to give you some perspectives, that really we're seeing the most emphasis in the space coming from Europe. They have established a climate neutral goal by 2050. The market for specifically these technologies is growing exponentially, but as you can see from the previous analysis, that there's still quite a bit of work to do to understand the role of these technologies. And so we're well underway in this trajectory to help drive those capital costs down, get the economies of scale, but still left to be determined how more and more of these technologies come onto the grid or are utilized by different consumers, the role that they will play. And it's exactly these questions that we are studying and trying to address in our initiative. We've got a number of other areas around the technologies. I'll just skip to talk about some other aspects of the research portfolio, but I'll stop there. And any perspectives anybody has on electrolysis, I'm not sure who all we have in the crowd today, but happy to hear your perspectives if there are any.
I had a question not about electrolysis, but about some of the plastic to hydrogen technologies that are being rolled out right now. And do you see that as, do you have any thoughts on that or on its kind of viability long term as another source for hydrogen?
So you mean combusting like residual plastic waste?
Yeah, there's a couple facilities that are being manufactured in California right now. And I guess it's like an advanced recycling facility that produces the hydrogen from plastic.
Right.
And so I didn't know if that was another area you all were looking at.
Yeah, we actually have a project funded through the US DOE that's looking at both, it's a biomass, coal, and plastics conversion, gasification technology conversion, and doing the engineering feasibility study on that. So I think it's, I don't remember the size off the top of my head, but it's, the details were just, the project was just notified of award a few months ago, so it's still getting underway. But
is that public?
Yeah,
is it
funded through, yeah.
Okay, yeah, I just wanted to read about it. Do you know the name of it?
It's I can follow up with you. It's positioned under the U.S. Coal First initiative, I believe.
Okay.
And I don't remember the funding opportunity number off the top of my head, but we can certainly grab it.
Sure. Yeah, it's really interesting. I had another question too. I know FERC is looking at its pipeline certification policy right now. And do you have any thoughts on kind of the importance of pipeline certification to look at kind of forward compatibility with hydrogen?
Yeah, that's a good question. It's actually the next slide. So
gotcha.
There's a lot of effort underway in the U.S. The DOE just launched a CRADA led by NREL, National Renewable Energy Laboratory, and other laboratories, EPRI and GTI, are participating to investigate the transition of natural gas infrastructure to blend hydrogen. And certainly there's a lot of challenges that come with that, but also some opportunity. So I gave you the hydrogen demand example. That was the international amount. If you looked at how much the U.S. produced in terms of hydrogen per year, I think it's about 10 million metric tons in 2018. If we made all of the natural gas infrastructure in the U.S. capable of holding 20% hydrogen by volume, that would require more than 4 times the amount of hydrogen we produce today just to meet 20% by volume. Because there's a lot of natural gas infrastructure. It's a significant amount of energy out there. But that 20% by volume, it leads to a 7% reduction in CO2 emissions because hydrogen has a lower energy density than natural gas. So you actually need more hydrogen to, from an energy perspective and an energy density perspective, to reduce CO2 emissions. So there's different trade-offs. You know, there's a lot of research studies, particularly in the UK and some in the US, that suggest that getting to 20% by blend in existing natural gas infrastructure is likely feasible, that metering equipment leak issues, embrittlement challenges, so hydrogen is very small gas, it can even permeate through the very fine pore structures that are in steel itself. That's kind of shown in this middle graphic here. But that at 20%, likely we could still maintain safety thresholds, and then there wouldn't be any disruptions or any major disruptions on in-use appliances. Now the challenge is it's not a lot of CO2 reduction, and how much is it going to cost to get that amount of, you know, if you're going to have to do any kind of retrofit, depending on, you know, it doesn't apply to all, you know, the U.S. Has a wide range of infrastructure in natural gas. Some of it's very old, some of it's quite new. The newer seems to be capable of handling higher blends, but it's integrated with some of the older infrastructure. So there's just a lot of nuances to consider there. But the DOE effort, it's a $15 million effort, is looking at specifically the U.S. infrastructure, and likely will play a role in helping to deploy hydrogen in the market. But long term, we've got to look much beyond the existing infrastructure, or, you know, either converting it and, you know, applying new techniques or laying new infrastructure to support hydrogen, or decentralizing the role of hydrogen, putting it in energy clusters or where it will be used, and then allowing for some time to achieve the expansion of networks specific to hydrogen, because they're limited right now in the Gulf, Texas, Louisiana region. Good question.
Thanks. We do a lot of work in the hydrogen space, so I'm always interested in learning about, you know, where it's going, especially as far as infrastructure.
Right. Right. Good. Another area that we're working on, end-use applications. So the hydrogen's got to go somewhere, and it's one thing to get it produced. It's another to convince consumers to take it and use it, and do so safely. So a lot of core areas around industrial scale gas turbines is an area that we're paying close attention to. These are smaller units, some of which have been using hydrogen as a fuel for a long time now. But as we convert to power generation scale, much larger technologies, machines, quite a bit of retrofits needed to likely accommodate hydrogen, not only to combust it, but also in the environmental controls aspect as well. And then looking at other parts of end use, so where batteries may struggle specifically is in some of these heavy duty transportation areas, long haul areas. Hydrogen is a potential option because you can store, from a miles driven perspective, a lot of energy compared to batteries, and then you don't have to deal with some of the issues with weight. Batteries are quite heavy, and having a lot of them in a truck would make it even less efficient. And refueling or recharging batteries of that size could take a long time. But there's trade-offs, battery swapping, and all those things. But still, a lot of emphasis in hydrogen to potentially convert over to fuel cell applications. And then understanding if the potential to use that in residential and commercial applications as well, for heating, for cooking. The UK is moving very quickly ahead. They've actually just announced a housing development project that will be fully heated and utilize hydrogen in their appliances, I think in the next 4 or 5 years. Some of you in the power generation space also be interested. We have projects underway to look at the combustion itself and designing a system integrated with hydrogen production, storage on site, and then combustion for energy services. So that's kind of what this one is. And then doing so at a large commercial scale and understanding the impacts, but then also looking specifically at some of the materials compatibilities in these combustion components. So when hydrogen is combusted, especially at higher percentages, produces a lot of moisture. And so understanding the impact of that moisture, which is more than it is today in natural gas from a materials perspective, the longevity, the operating cycles, any maintenance impacts need to be studied very carefully. The U.S. relies on and will likely rely on a significant amount of gas turbine fleet moving forward, either from a generation perspective or from a capacity perspective. And so if we're thinking about using low carbon fuels such as hydrogen or even ammonia, we've got to be very sure we understand the impacts of those fuels. You'll also see coming from the LCRI over time, projects and initiatives. I mentioned some of the green hydrogen and the natural gas transportation examples, but also looking at much more areas. We believe that one of the strongest ways to jumpstart this transition, this transformation to a low carbon future, is to bypass this chicken and egg, scenario, put the technologies in the ground, do the demonstration. We're seeing that worldwide. We'll contribute to that as well. And we have a very robust sponsorship of organizations who are funding this initiative and helping to guide us. And we're very excited for the work that we've set out. We're pretty much just starting the process of the project this year. It'll continue for the next 5 or so years. So much more to come from that. So that concludes the content that I had. I'm happy to, with the remaining time, take any questions or hear other perspectives.
How about any questions for Jeffrey? We've had a few questions along the way. Jeffrey, this may be a little bit out of field for you, but we see a number of cities, governmental units, states and that adopting zero carbon or carbon neutral objectives. I'm wondering how many of these objectives are aspirational, or how many that you see from a scientific standpoint are fact-based and realistic for these cities or counties or units of government to be able to attain. You have any thought on that?
So I think it's complicated, honestly, because it's important to set the goal, and where we've specifically seen the decline in interest for hydrogen over the years. I mean, it comes and goes in waves. A lot of things do. Various hype cycles. The difference this time, it appears, is that we now seem to have a purpose for hydrogen and low carbon fuels to serve, rather than an alternative for them in a world that doesn't say it needs it. And so by saying we want to reach this goal, you're essentially saying I'm open to the idea for change. And so our perspective is, let's go explore what those options, and give as many options as we can, because as we've shown in our analysis, the more options we have, the lowest cost, the more likely we are to adopt those changes. Now, the way you could do that is up for debates by policymakers and economists and engineers like myself. But if you look at Europe's model, they have tied a lot of their decarbonization efforts to economic recovery from the impacts of COVID. And so they have said, hey, now's the chance. We need to jumpstart our economy. We're going to put in money specifically towards reaching these carbon reduction targets. And we are going to go out and we are going to use public dollars to say, if the public has agreed, because we've signed up for these goals, we've enacted these policies, these laws, you've voted for these people who made this stuff happen, this is our way to say we're going to actually do it. And so Europe's approach is largely, and I'm drastically oversimplifying, but let's put the money in these areas and make the market develop by going forward with these demonstrations. So you're going to see a lot of large-scale hydrogen deployment. There's tons of announcements. 3 to 5 years from now, we expect to see, as I showed you, all of these new technologies come on board in the technology space. We're looking at that and saying, okay, if that's the case, if that further drives down cost, if we see those policies take shape in other parts of the world, as we see these energy systems start to integrate, what it's done is it's jump-started other parts of the market. So now in the Middle East, you see Saudi Aramco has converted some of their steam methane reforming hydrogen units to deploy CCS. They have now produced blue hydrogen, we call it. They've converted that to ammonia. They're shipping that to Japan. Now the world is starting to actually utilize, of significance, new fuels, or at least it's saying it's going to. So now whether we can continue on the path as it is, you know, the crystal ball is still fuzzy on my end. We are projecting in this initiative will be very clear to suggest how and where technology deployment options could help continue that pathway, make it affordable, reliable, and resilient to the perspectives that we have for energy today. But we think it has to start with a commitment, and I personally don't see that there's any one obvious solution to any of these problems. So I think it's not a bad thing to not have those roadmaps yet in place. You see that in some places, California, New York, they have very specific targets and roadmaps that they're developing. But by and large, we're still in the nascency of this transition, but we've got to move a lot quicker than we have in the past.
How about other questions for Jeffrey?
Sure. I had another question. And thanks for fielding so many from me. But I know I read about the kind of integrated hydrogen production and use grid that they're building at, I think it's UT Austin. But talk about communities trying to implement hydrogen. Do you know if are you aware of any other kind of community hydrogen microgrids that are being built right now in the U.S.?
Yeah, you should. Oh, in the U.S.
Well, I'd be interested outside of the U.S. too, if there's some good examples there.
Yeah, the UK has, through Northern Gas Networks, the H21 project. There's a ton of information, publicly available information on various studies there, utilizing it specifically in commercial and residential areas.
Gotcha. Thanks. Yeah, it's a pretty exciting area right now. And then do you have any thoughts on kind of ammonia versus hydrogen? Because I know that's one of the things people are sort of debating which way they want to go as far as production and transportation.
Yeah, there's trade-offs abound because ammonia a little bit easier to transport because it's easier it's primarily in a liquid form. The world is used to moving large amounts of ammonia, shipping and storage, and the general public doesn't see a lot of it, but from an industrial perspective, it's not all that complicated. The challenge is, though, with the toxicity, you know, people rightfully so are concerned about, you know, environmental aspects, human and other aspects of any potential release. Same with hydrogen and combustion. People think of, you know, Hindenburg and, you know, all those types of things. Unfortunately, we're marred by, you know, global events. They bring focus to these areas. Moving past is hopefully the goal, and then doing so safely. But from an ammonia, we're seeing a lot of that conversation take place in the international shipping area. We're seeing commitments there, which are actually driving some very near-term transitions, where they're considering ultimately a few pathways, either through methanol or ammonia, as their fuel for onboard engines. And so, where that ammonia comes from, it's a subject of another hour-plus conversation, but largely not likely to have any significant production changes because ammonia primarily comes from a natural gas source. The Haber-Bosch process has been around for a very long time. It's very efficient. Challenge in this economy approach, this decarbonizing approach, is that it might be too big. It might be too efficient at a larger economies of scale if you don't have fertilizer plant or something else nearby to take use of the vast production quantities that come from an ammonia system, then is it affordable to go to lower production routes? So we're studying those as well, in addition to other, using hydrogen, because there's 3 hydrogens in an ammonia molecule. So taking nitrogen from the air, combining that with hydrogen, perhaps produced from another low carbon source, likely a few decades away from having a commercially viable option there, but definitely something worth looking into.
Got time for one more question. Do we have another question out there? Going once, going twice. Thank you, Jeffrey. Very well done. That was just a really amazing overview of the topic. Jackie is Director of Power Generation, Regulated Operations at Dominion Energy. So she joined Dominion in 2010 after graduating from University of Tennessee at Knoxville with a nuclear engineering degree. She subsequently earned an MBA at Virginia Commonwealth University. She's been responsible for nuclear design, hourly trading, electric market operations, and in August 2020 became Director of Power Generation, Regulated Operations. So Jackie, is that you?
Thank you. Yes. All right.
All right. So let me tell you a little bit about who you have here, okay?
Okay.
I'll give you a quick rundown. Rather than we got, let's see, we've got about probably 16, 17 people online right now. So rather than have them all come on and introduce, we have people represented from Framatome, Siemens, and then Carolina Gas Transmission, with which you might be familiar, Electric Cities, Central Electric Membership Corporation, they're a electric cooperative, Westinghouse, Electric Power Research Institute, City of Charlotte, Duke Energy, Pillsbury, which is a law firm, North Carolina Advanced Energy Corporation, their research organization, and RNG Futures. I think I've covered everyone. So you can see you have a very diverse group: power, natural gas, some renewables. You have people from utilities, people from manufacturing, and people from research.
Awesome. Sounds like a good crowd.
It is. All yours.
All right. Well, I will show my video for just a second to say hi, and then I'm going to turn it off just for bandwidth issues. And I've had experiences where my video gets all finicky and frozen. So hello, and then I'm going to turn it off. All right. So today I am going to be discussing really PJM 101 and PJM markets overview. When you're in the Carolinas, you're not part of PJM, but Virginia starts the PJM territory. So we're just going to go through what we do in PJM and how it's different from what you guys do in the Carolinas. So first, let's talk about, you stole my thunder here for a little bit. Who am I? So Jackie Vitello. I am a University of Tennessee nuclear engineer. If anybody else is from University of Tennessee, chime in on the chat. I'd be interested to see how many vols we have in here. Probably none, but you never know. Graduated in 2010 and then came straight to Dominion. I had 2 internships at Dominion in nuclear analysis and fuels. Oh, did somebody chat? Is there? Oh, yay. Good job, Jessica. You're a Tennessee vol. That's awesome. Graduated 2010. Met my husband actually at work. So he is also a nuclear engineer. So we call ourselves the Dominion Nuclear Family. So that's us right there. We are on the cover of the 2019 annual report because we have an electric minivan. So they asked for volunteers with electric cars, and we said, that's us. So that's our family. We've got 3 very little children. That was taken about a year ago. So now they're 2, 4, and 6. But they keep us busy. And I was trying to think of things that related me to the Carolinas, and a little unknown fact about me. I spent a summer at Brevard Music Center. Has anybody heard of Brevard in the chat? Anybody heard of Brevard? It is a very famous music center if you are really good at playing an instrument. It's in the top of like Interlochen, Brevard. I spent 10 weeks at Brevard Music Center. Let's see. Oh, 10 minutes down the road. Good. Yeah. So I went out there, and thanks to Brevard, I got 8th chair out of 9. And I said, oh my goodness, I cannot play clarinet for the rest of my life, so I guess I'll be an engineer. So you're welcome to North Carolina. This is why I've ended up here. But I did really like the mountains of North Carolina. So, all right. Oh, that's not gonna work. Okay, here we go. Let's talk about PJM and markets overview. First, what's an RTO? What's an ISO? So RTO stands for Regional Transmission Organization, and ISO stands for an Independent System Operator. Basically the same thing. They're tasked with the general mission of coordinating the bulk electric power system in a safe, reliable, and secure manner. So if you look at this map, you can see that there are 7 operating RTOs and ISOs in the domestic United States, and there are 2 in Canada. And basically they serve as an independent third-party operator of the transmission system. And so they're there to develop and facilitate competitive markets to balance the load requirements with the generation necessary to supply those requirements in a cost-effective manner. So the goal of all these ISOs and RTOs is get the least cost generation on the system that you can and make it cheap for people to turn on their lights, basically. We do have a few government entities that look over us. We have NERC, which is the North American Electric Reliability Corporation. And NERC focuses on security, reliability, and adequacy of the bulk power system. So really, if you think about NERC, it's all about reliability. They don't want any blackouts, brownouts. And so trust me, Texas recently, NERC is all over that. Then we've got FERC. And FERC is the Federal Energy Regulatory Commission. And yes, they care about reliability, but they're more focused on the fair and competitive markets and just and reasonable rate treatments. So if there's any type of market manipulation going on, or if somebody's getting paid too much, if you think of the money side of it, you're going to be hearing from FERC, not NERC. All right. Then all of these ISOs and RTOs have something called an independent market monitor. We call it the IMM, or monitoring analytics. They all have different names, but basically it's, Big Brother watching over you. They're there to focus on ensuring competition and non-discriminatory considerations in the RTO market. So they're watching over both, the actual utility, but they're also watching over the RTO ISO. So, we're part of PJM. They're questioning PJM's actions, but they're also questioning the utility's actions. And they're just trying to make sure that everybody's playing the same game and everybody's playing a nice game. So that's the IMM. All right, so Dominion Energy, we participate. We're mostly in PJM, right? Because we are mostly Virginia. But we also have solar units out in California ISO, and then we have our nuclear unit in Connecticut, so that's why we are also in ISO New England. All right, so, back on this other slide, you're like, well, what about the rest of the country here? What happens there? Well, you guys are part of the Southeast, and then you've got the Northwest and Southwest. And as you know, you're responsible for your own load and your own generation. So for Duke, you guys could probably tell me better than I can tell you, but when you probably have your own control room and you say, I'm going to start whatever generation I want today, and it's going to meet my load today. And you really don't have necessarily a market that you're calling into, and they're not the ones deciding which generation to start up. You guys are. So that takes us to the Southeast Energy Exchange Market. And once again, the people from Duke probably know more about this market than I do too. But recently, back in 2020, this Southeast Energy Exchange Market potential was announced. It went to FERC in February of 2021, and they requested FERC approval in 90 days. So May of 2021 is when we should hear if it's approved or not. And Dominion Energy South Carolina is part of this. But keep in mind, I'm Dominion Energy Virginia, and even though we're both Dominion Energy, I have strict rules not to talk to Dominion Energy South Carolina. so I don't talk to anybody in South Carolina. But anyway, if it gets approved by May of 2021, it could go live in the first quarter of 2022. So some of these founding members, as you can see on this map, you've got Duke, Dominion Energy South Carolina, Southern Company, TVA, you name it. And right now they do bilaterals between each other, but they pick up the phone and it's a very manual process. And so what they're asking for, they're not asking to become an RTO or an ISO. They still are going to control their own gen and load. They're asking for more technology, basically. And so it's going to be a 15-minute energy market. It's going to be the first of its kind for the region, and they're going to use technology and advanced market systems to automatically match participants with low-cost energy to serve customers across a wide geographic area. So the new SEAM, they're going to call it SEAM, Southeast Energy Exchange Market, platform will facilitate sub-hourly bilateral trading, allowing participants to buy and sell power close to the time the energy is consumed, utilizing available unreserved transmission. The exchange is an extension of the existing bilateral market. So like I said, they currently trade with each other. It's just going to be an upgraded technology system. The SEAM members will maintain local control of their generation and transmission assets, and participation is voluntary. So you're not going to have a main control room authority, basically. You're going to keep your same control rooms that you have now. Does anybody have any other insights about this market that you'd like to share with the group that I don't even know about? Anybody from Duke or anybody that, does anybody have anything they'd like to add about this Southeast Energy Exchange Market? And it's okay if you don't. It's all a very new concept. All right.
Hey, Jackie, this is David.
Mm-hmm.
I will add for the group that this proposal is a little different from that which utilities typically propose. This is a utility consortium, and from a regulatory standpoint, it's being examined not at the state level as a rate case, but it's being examined at the Federal Energy Regulatory Commission, which gives it it kind of falls into a different area than what typically utilities deal with, at least the utilities here in these states. Also, I don't want to say controversy, there's a fair amount of local interest with regard to whether this should be implemented and how it's implemented. And there's different proponents in the Carolinas and in the Southeast that want basically an independent system operator, regional transmission operator type of approach, just like you have in PJM. They'd like that instituted here, because that would allow them to to develop power projects and build them without the rigors that they have right now and sell into an open market. And that's not what would happen with the SEAM approach. So what we're seeing is a good deal of activity at the local level that it is working to either provide an alternative to this proposal or to change this proposal or to oppose this proposal. But interestingly, most of the advocates are geared to operate at the state level, and this is at the Federal Energy Regulatory Commission level, which is an interesting change for the folks here in our area.
Right. I wonder if the reason that they're going to FERC now is that eventually it will become the RTO ISO level. That's at least in my mind.
I think that why they're there is because it clearly involves interstate commerce rather than utility operation within a single state.
Mm-hmm.
So I think it very appropriately is at FERC, but I think a lot of the stakeholders that are interested in a concept similar to this, like an ISO and RTO, thought that it might start at the states. And interestingly, even the North Carolina Utility Commission looked at this and said, it's beyond our jurisdiction, and didn't do anything with it.
Yeah. Interesting.
So more to come.
More to come. Yeah, we'll see what they say by May, I guess, of 2021.
Yeah, quick question. This is Joseph Evans. Just you may have already covered it, but why is Florida not in this map?
Good question. I do not know.
Do you think I know Florida has some real serious interconnection issues with the limited number of transmission lines that cross into Georgia? Do you think is that maybe part of it?
It could be.
Okay. Yeah. Well, thank you. It was interesting. So thank you.
Yeah. I'm not sure. This is all new territory to me also. Yeah. It's almost like Florida kind of looks like a Texas where they want to be on their own almost when you put it in that perspective. Yep.
Yeah. Another place that gets hurricanes. Might not.
That's right.
Yeah.
All right. So here's what PJM looks like. We do also have a lot of different utilities. You can see that PJM started in 1927 stands for Pennsylvania, Jersey, and Maryland. And then you can see a bunch of people have added onto the system over time. Dominion joined in 2005, and Kentucky was the latest one to join in 2013. So there are different NERC regions, and PJM is part of two of those regions. We are part of Reliability First and also the CERC region, and you guys are also CERC. But this is the NERC map that you've all probably seen, and Texas, as you all know, they're their own little region down here. Oh, and maybe this is why, to your Florida question, they are their own NERC region, so the Southeast Energy Market would just be the part of this CERC region. That's a potential.
Okay, thank you.
Yeah, just a guess. All right, so like I talked about a little bit before, for this RTO model, when you think about who's working on your control rooms, if you, like in the Southeast example, all of your utilities are going to have your generation operator and transmission operators. But when you look at PJM's model, PJM has all of these different people working in their control rooms, but then every member company also has all of these different people working in their control rooms. So PJM has the main balancing authority and reliability coordinator, and they're the main transmission operator. But then you go to every member company, and they also have to have like a system operations center with all of their transmission people. And they have to have a market operations center with all of their generation people. So it splits it up where PJM has the main authority, and then all the member companies also have workers. So if you look at PJM statistics, we do have 21% of the US GDP produced in PJM. So there is a lot going on in PJM. There are 65 million customers served, and our peak load in PJM hit 165,000 megawatts back in the summer of 2006. The generating capacity is at 176,000. There's 82,000 miles of transmission lines, 13 states and DC. So lots going on in PJM. And just for some comparison here, this is the world map. You can see PJM's at 165 gigawatts, right? But MISO in comparison, so the Midwest ISO is at 98 gigawatts. China over here, they have a RTO that's at 544 gigawatts. That's huge. But most of the other ones, you know, PJM is pretty big compared to most other RTOs in the world. Okay, so let's talk about the energy market side of it. This is the fun part. So the wholesale electricity market consists of 3 different markets, and they're all different buckets. So you really have to think of them in 3 different ways. You can't really combine them. And that gets a little confusing to people. They try to say, well, I didn't clear my capacity market, so I can't participate in my energy market, but that's not true. You got to think of them all very differently, like 3 different buckets, okay? So you've got your energy market, and that's day to day. It's the system for purchasing and selling electricity using supply and demand to set the price. That is your everyday operations energy market. The capacity market, this is where your resources are compensated for investing and delivering capacity during a commitment period to meet the region's reserve margin requirement. This you have to think about as a like 3-year delivery period. I mean, it's a 1-year, well, I said that wrong. It happens once a year and it's for 3 years out. So you just have to think of it as an investment in your units. And if you clear the capacity market, that means that PJM needs your unit 3 years from now, and they're willing to pay you to be online 3 years from now. Then the third bucket is the ancillary services market. And this is the services that ensure the reliability of production and transmission of electricity. So this is everything extra. It's like the black starts and the regulation and all the things that you spend money on your equipment so that it can do nice things for the grid that isn't necessarily required of you to do. But because you spent that extra money and you can do these nice things, that's where you get paid this ancillary money, okay? So for the energy markets, there's 2 distinct markets within that. You've got your day-ahead market and your real-time market. And this is how my career started. So after the whole nuclear phase, I started as a real-time trader in the real-time energy market. And what you do, when you have an hourly trader position, this is in your market operations center. So you can either be called an hourly trader or you can be called a generation dispatcher. It's a 24-hour desk. So you're working 12-hour shifts. You work from 6 a.m. to 6 p.m. or 6 p.m. to 6 a.m. And you sit at the desk and you watch 5-minute prices. So every 5 minutes, PJM is going to send you something called an LMP, which we'll go over later. But it is a real-time market, and you are telling your units where to be or how many megawatts to produce based on the cost of that unit and based on where LMPs are. So that is your real-time market. It's actually happening. You're actually moving units around, and that's why we call it physical. And then you have something called the day-ahead market, and it's just like that. It's the day before the actual operating day. So this morning, we offered in all of our units for April 1st because today is March 31st. Now, when awards, we call them awards, when awards come out for tomorrow's operating day, it is purely financial. I have not flipped the switch on any of those units. I have not run a single megawatt. So everything I get paid in the day-ahead market is 100% financial. When I move over to the real-time market, that's when it becomes physical. But whatever I do in the real-time market affects what I get paid over time. Okay, so market clearing prices and awarded megawatts are the result of PJM's load forecasts and the least cost solution to meet the projected load requirement. So what PJM does is they look at all the offers that people put in, then they look at the load curve and they clear people's megawatts and they say, okay, I need 100,000 megawatts during hour ending 12. And so, and that's another term we use is hour ending 12. That means 1100 to 1159. So hour ending 12, I need 100,000 megawatts. So they choose the cheapest 100,000 megawatts. And there's a lot of other parameters that go into that. You know, you have min run time, startup time, all of these parameters. So they choose the cheapest. And if you get an award for that hour, that means they expect you to be running for that hour. All right, there's two different types of offers that we offer each day. So you have a cost offer and you have a price offer. So in PJM, they have all these manuals, and for the cost offer, you're not allowed to play with it at all. You have to follow PJM's manuals and it has to be exact. And PJM and IMM, they look at all of your inputs and they look at your fuel costs and they look at your emissions. They look at your heat rate and your heat input coefficients. And if you offer higher than your true cost, they report you to FERC and then you get fined millions of dollars, potentially. But it's very, very, very important that you offer at your true cost of your unit for your cost offer. And that's because if there was some type of emergency on the system, or for some reason they really needed you, then they would cost cap your unit. That's what it's called. So they would be able to give you an award even though you were outside of the least cost option. And then they would make you whole to your cost offer. Now your price offer, you can do whatever you want with your price offer within reason. So if you have your cost and then you say, well, I have a big, like if I run too much, then I'm going to need to spend X amount on maintenance, or I have this emission problem going on, or, you know, whatever other reason it may be. So I need to add a few dollars to my price offer. You can do that to your price offer and they won't, you won't get in trouble for changing your price offer. And usually you get awarded on your price offer. So cost and price offers, we kind of talked about this, but you've got a startup cost. So if you're offline and you need to start up for the next day, it could be a $10,000 cost, it could be a $100 cost. I mean, they will take that into consideration when they give you an award. So certain units have higher startup costs than other units. If you have a CT, for example, that's like a quick start, that startup cost will most likely be less than a really big coal unit or a nuclear unit or whatever it might be. So you're not going to see these really big coal units starting up every single day and shutting back down. You also have fuel costs, so the cost of fuel, and that also considers your heat rate curve. You're allowed to put your variable O&M costs in your cost curve. You have emission-related costs, so things like NOx and SOx, and right now, actually, Virginia joined RGGI, so I would consider that an emissions, so a CO2 basically emissions. And Virginia, so speaking of RGGI, that we were the 11th or 10th, I think we were the 11th state to join RGGI, and it's been a very interesting change. We joined on January 1st of 2021, and it added a good deal to our cost curves there. Then there's also other opportunity costs. So you have run hour limitations for operational or environmental reasons. So you might, if you have an oil unit, you might be able to only run 2 hours, or you only run 4 hours, or you might only have a tank that holds a certain amount of oil. So you have to consider all of these different environmental things in your offers. Then every single day PJM uses this website called Markets Gateway. You have to update your operating parameters. So you have to tell PJM what your eco min and eco max are. So an eco min means economically, I'm willing to go to this minimum level on my unit. If I go any further down, I might trip my unit. And so PJM likes to know how far down, what's the minimum on the system everyone can go to. And that's really important in the spring and the fall on very mild weekends or overnight at like 2 in the morning or 3 in the morning. How far down can people get? Because we run into these problems where we have too much generation on the system and people can't go further down. All right, then you also have Eco Max, which is the same thing except the other way around. How high can your unit go? Then you have emergency min, emergency max. Some units, I guess, can go even higher or even lower without tripping, I guess. And then you have min run, max run, and that is mostly, like most units can run 24 plus hours, right? And most units can, well, not all units, but you might have a unit that, like a coal unit, for example, you don't want to run that unit for just 2 hours. And so you might put a min run time of 24. So you can tell PJM, like, if you turn my unit on, you need to keep this unit on for X amount of time. Those are the types of things that you have to tell PJM that in your type of market where you don't have somebody else telling you what to do, you can do whatever you want with your units, but we have PJM telling us what to do. All right, LMPs. LMPs are locational marginal prices. They're made up of 3 things. You've got your generation marginal cost, and this is the clearing price for the entire RTO. So everybody has the same marginal cost for every 5-minute segment, okay? The thing that makes it different for each location is the transmission congestion cost and then the cost of marginal losses. So you're going to see a map here in the next slide. Every generating unit that we own and every generating unit that PJM has, they have this locational marginal price, and every 5 minutes it's going to be different from the one next to it. And it's all based on these transmission congestion costs. So here it is. Here's your PJM RTO LMPs. We used to be called hourly traders because we used to settle on an hourly basis. But back in April of 2018, they changed their minds on the settlements. So day ahead settles at an hourly basis, but real time settles at a 5-minute basis now. So when you are working the hourly desk, we still call it the hourly desk, you really are concerned with the 5-minute LMPs. If you see a spike in prices and your unit is sitting at min load, it is to your benefit to move your unit as quickly as you can to full load or base load. So that process would be you would be looking at your screen and you would say, oh, prices just went to $100 or whatever they went to. And you would pick up the phone and you would call your control room. So you are the middleman basically between PJM and your generation control room. You'd call them and you'd say, go to full load. And your station would say, understand, go to full load. And then they would go. And so part of your decision making is how long do you think LMPs are going to stay there? How long do you think your unit is going to take to get to full load? You know, if you have a really slow moving unit, do you actually move them? So there's a lot of decision making going along with spiking, or I mean, you can see negative spikes too in LMPs. So definitely a fun job. All right, here's your marginal cost clearing prices and your bid stack. So this is how they come up with day ahead awards. If you offer your unit, so this is pretend you have 5 units here. And your supply stack bid, you've got 5 units that offer at $20, $40, $60, $80, and $100, okay? And you need about where that red arrow is. That's how much energy you need. And it just so happens that, that's where your clearing price is going to be. Anybody below that stack is going to get an award. Anybody above that stack is not going to get an award, okay? So if I offered at $20 and the clearing price was $60, then I'm going to have an award, and my day ahead award is going to be $60. And so I'm not going to get paid $20. I'm going to get paid $60. That's also important. Even though I offered in at a lower cost, I'm still going to get paid whatever the clearing price is. Okay. This is a typical summer curve because you have one hump throughout the day. If you have two humps, I should have included a picture, I guess, but if you have two humps, that's like a winter curve. So this is a summer curve, and this is just a depiction of the types of units you're going to see. So renewables are your first and cheapest units, right? So they're $0. And actually with RECs and you could see some of those renewables at negative prices, right? So if you're getting paid to produce energy, you're not going to offer your unit at $0 most likely. You probably will offer your unit at -50 or negative whatever you're getting paid for it. So that's why, like in California, for example, sometimes you see negative LMPs throughout the day. So renewables are first. Okay. Then you've got nuclear, and technically nuclear is $0, right? And the thing about nuclear is you're not going to offer your nuclear unit economically. So what I skipped over is how you offer units or the status of your unit. You have 4 ways to tell PJM your status. You can say you're economic, and that means that I'm available to run if you want me to run. You can shut me down if you want to shut me down. And I'm just here to do whatever you want to do with me. Or you can say, I'm unavailable. I'm in a maintenance outage, a forced outage, a planned outage, but you know what? If you make me unavailable, you better have an EDART ticket out there. You better have some way to tell me why you're unavailable. Because if you don't, that means you're violating the tariff. Because we have a must offer requirement on capacity resources. Okay. The third way is to must run your unit. So you can say, I don't care if I am way out of the money. I want a day ahead award. So I will lose whatever I'm going to lose, or I will make whatever I'm going to make. You are forced to give me an award. And that's how nuclear units usually offer into the market. They're not willing to shut down, right? You load your core, you come online for 18 months, and then you refuel. So if you shut down a nuclear unit, it's not like they're saving any fuel. So nuclear units are going to be must-run units. So they are considered base load. So if you see like the bottom green and the 10, 15, 20, that's what you would call a base load because it's covering your base. And you see that 2, 3, 4 in the morning where it drops. And that's where I was talking about the eco mins overnight, where how far down can you push all of these units? Okay. Then you've got, so obviously this is like a crazy hot summer day because we usually don't see $120 prices. This maybe was a few years back, but nowadays in our hot summer days, we maybe see $30 as our peak. In the winter now, if you have crazy gas prices, now maybe you'll see $120, but not very often. So next on the stack of units, you're most likely going to have a combined cycle, and it's driven by gas prices here. So this is assuming like a $2 or $3 gas price. If in the winter, again, if you see $5, $6, $7, $8 gas, then you're going to flip your combined cycle and your coal here because coal is going to be break even on like a $3.50, $4 gas. So combined cycles next. They're going to get dispatched next. Then you have your coal units. And if you've got all your combined cycle units running, if you end up getting, $40, $50 prices, then maybe your coal units are going to start getting called on. And then lastly is your CTs. And your CTs are usually oil peaker units. And that's, just those peak 4 hours in the middle of the afternoon where it's $120 and they only need you for 4 hours. So that's when your CTs would come online. Okay, and this is kind of the same curve, just in a different look. You can see this right here is your variable O&M costs. And then this is your cumulative summer capacity megawatts. So this is all of PJM for 2019. It's the entire PJM supply curve. So it's every unit in PJM. And you can see how much wind and water and solar there is. And then the yellow is all of your nuclear, uranium, it says here. And then you've got all your gas, and slowly it gets into your coal, and then you've got all your oil up here, okay? So these lines are your normal load days. So this is like your average load around 90,000. Your peak load for 2019 was 151,000. And so on a normal-ish day, you're going to be running most of your nuclear, whatever your renewables are online, most of your gas, and potentially some coal, which is a normal day. Okay, the Market Operations Center. So every day is very proceduralized, and we work on a very tight schedule. And so technically the Market Operations Center is both day ahead real time, like we talked about. Day ahead offers are due by 11 a.m. So if you work the day ahead desk, that means you're working about 0500 to 1500 every day. It's a 10-hour day, but you're working 7 days a week. You get in at 0500, offers are due by 1100. The awards come out around 12:30 or 13:30, and then you have to do the reoffer. So once awards are out, then you can reoffer. Reoffer ends at 14:15, and then real time picks it up around 18:30, and then real time really picks it up at midnight, right, when the actual operating day begins. So. All right. If you're sitting in the box, we call it the box, the MOC, then you are, I call it the middleman, because you are talking to everybody. It is a really good place if you like to talk on the phone. You're talking to the power generation stations. You're constantly getting updates on their availability, capabilities, any change of status that they have. If they trip offline, you pretty much have to get their status as quickly as you can because you're in charge of telling PJM what just happened. So you have to call PJM. Then you also have to pay attention to your load. We are a vertically integrated utility, so we also have DOM LSE. So there are load characteristics. You have to pay attention to the weather, your demand forecast, and then on top of that, we also have to pay attention to our regulation awards, reserves, reactives. We have a lot of reporting requirements for black start units. So that's more of the ancillary services that I'll get into in a little bit. Lots to do in the MOC. ACE. ACE is something big that we look at. It's all about supply and demand. All of the exports and losses and load, that's your demand. And then all of your power generated and imports, that's your supply. And so the RTO is responsible for maintaining that power system control throughout the day. It's all about maintaining the 60 hertz across the grid and keeping your ACE around 0. When you turn those lights on, we want them to turn on. The lots can go on throughout the day. You've got generation unit trips. There's transmission line outages that happen. Extreme weather. I'll say that the most interesting days on the desk are days with extreme weather. If you work a snowstorm or if you work, like I worked Hurricane Sandy, I worked the polar vortex of 2014 or the cold snap of 2018. Those are the fun days to be on the desk. I mean, well, fun is a subjective, I guess, but those are the interesting days. It's the days that you remember forever. And so PJM probably remembers them too, but in anticipation of those days, you always have to keep reserves on your system. So PJM is required to keep the largest generator as their reserve. So we actually have the largest generator. It is Greensville Power Station. We have 1588 megawatts is their ICAP. And so they are required to keep 1588 megawatts as reserves just in case they trip offline. So we've got communications. We kind of touched on all of these MOC requirements already. The timelines, the 1100 deadline for day-ahead awards, all of the communications. Resource limitation reporting is really big during cold weather events. And this really picked up after the polar vortex of 2014 when we ran a lot of our oil units and we found demineralized water was a big concern. So PJM has really increased their cold weather game on just anytime we have a cold weather event, really. They are really concerned with resource limitation reporting. All right, so we kind of talked about day ahead versus real time, but here's an actual math example. So pretend you have 1419 as your award, and it's a $20 award. This is just pure math. You're going to get paid 1419 times 20 for that 1 hour, okay? So you're going to get $28,000 for doing absolutely nothing. Then, in real time, the unit trips, and therefore you have a real-time deviation of 1419 because you're sitting at 0 megawatts, right? In real time, sadly, your real-time LMP comes in at 75. So now you have to pay PJM back $106,000. So your net loss for that 1 hour is $78,000. So that's how quickly something can turn in the real time. Now you have no control over having a forced outage, right? But you have control over minor megawatts. You know, if you see a $75 price spike and you're sitting at 1400, you should try to get your unit to at least 1419 or higher. So the real-time desk is responsible for all of these little megawatts and all of the price spikes that need to be watched. And this, to make it more complicated, I guess, it could go the other direction too. You know, you could have a negative LMP, and so it could go the opposite direction, and it could work out for you. It usually doesn't, but it's fun to look at these numbers sometimes. Okay. So that was all the energy market portion of it. Let's move on to the capacity market now. So this is the market where I'm looking 3 years in advance, and it's completely opposite of the energy market. So this is the market to address advanced generation for future times, okay? We're looking at unforced capacity as opposed to installed capacity. So your forced outages matter for your capacity market. Approved planned outages and maintenance outages do not count against your E4D. Here's your capacity market schedule. 3 years in advance, I'm going to look at that delivery year. So this is a little weird because we're a little behind on our capacity market. A lot has happened, which I'll go into in a second. And I'm running a little late on time, so I'm going to talk fast here. But on a normal year, so it's currently 2021, I should be looking at my 2024-2025 auction, okay? And then you have all these little incremental auctions along the way to get you to your delivery year. All right, normal capacity market and your VRR, that's your variable resource requirement. You have a supply and demand curve. You have all of your generation offers that come in here. Let's see if I think I can do this. Okay, So all of your generation offers here, you have this VRR curve. Wherever it meets in the middle, that's your clearing price. And people really care about their capacity clearing price because it pays you a lot of money. So the 21-22 base residual auction, this is real data. Everybody cleared at $140 per megawatt day. That was the last auction that we had. Now we are 2 years behind on our auction schedule, and our next auction is, like 6 weeks from now, May 19th, 2021. That is the 22-23 auction. The reason we are so behind is that we had this big FERC MOPR issue, minimum offer price issue. So that has majorly compressed the auction. The next 5 auctions have been released. So you can see here that we're going to try to get caught up. By 2023, we should have this 26-27 auction. All right, capacity market. If you hear about Texas, they talk about how they don't have a capacity market. We think a capacity market is a good thing, especially during shortage events. They do have a penalty structure for non-performance. So if you don't perform, if you're in a forced outage, you have a penalty rate of about $3,600 per megawatt hour. And that's something that Texas didn't have. And you could see that from a few months, or I guess it was only a month ago. There was really no incentive to perform well during that cold weather event. There was no incentive to add equipment or, winterize anything. So we have a very big incentive. That penalty rate would really hurt your units if you got charged that. Now, this was all it was all kind of caused by the polar vortex of 2014. We did not have a penalty structure for the polar vortex of 2014, and we saw huge forced outage rates during that time. So PJM said, let's come up with this penalty structure. And then we had the cold snap of 2018, and things looked much, much better. People performed a whole lot better. This started in 2016, and so since it started in 2016, it's been 5 years, we have had one PAI, and that's a performance assessment interval. It has lasted for 1 hour and 45 minutes, and it hit 4 different zones, including Dominion. So it was not very fun for that 1 hour and 45 minutes. So like I talked about earlier, minimum offer price rule, December of 2019, it really hurts the capacity market for new resources. Basically, it says that if you're a state subsidized resource, you're forced to offer into the capacity market at a very high price, which means that you're very unlikely to clear. So there is an alternative to your normal capacity market, that VRR that I talked about earlier, and it's something called the FRR. And so a lot of participants have been saying that if MOPR stands, the FRR is an alternative that they would consider. And the FRR takes you out of the clearing price of the capacity auction. And it basically means that you are going to self-supply your own LSE. You're not going to get a clearing price, so you're not going to get capacity revenue, but you're also not going to pay for your capacity expenses. It's just a different market. But if a lot of people pulled out of the capacity market and went FRR, it would have some big implications to PJM's capacity market in general. You would still be considered a capacity resource. You just, you wouldn't participate in that VRR curve. So impactful events, we talked about the 2014 polar vortex, huge forced outage rate, really bad for PJM. We didn't experience any blackouts, thankfully, but it definitely changed the way that they thought about the penalties. So how did they address it? They came up with the penalty structure. Ancillary services. This is, regulation, reserves. anything extra that you do for your unit, you're going to get paid just a little bit of extra money. So operating reserves, if you can start your unit in less than 10 minutes, that's called non-synchronous reserves. If you can get extra megawatts within 10 minutes, that's called synchronous reserves, and you'll get paid extra money for being able to do that. Black start units, reactive power, reactive supply, all this is very important to PJM. How quickly you can follow the market, this is Reg D versus Reg A. They will pay you extra for all of that. We just talked about that. All right, current issues and topics. So minimum offer price rule. This is the big one, of course. Nobody likes MOPR, not even FERC. We'll see if that changes with the new administration or not. And then PJM Carbon Pricing Initiative. I kind of touched on it earlier with RGGI. Virginia joined RGGI because of the Virginia Clean Economy Act, but PJM's also talking about, if certain states join RGGI, does that really help anything? Because if my units get called off because they're producing too much carbon, does that really cause other units in the other parts of the RTO that are less efficient, are they going to get called on and maybe have more carbon emissions than my units? And so it's not exactly, I don't want to say fair, but do state carbon policies affect the wholesale electric markets in the right way? Or should there be a PJM initiative so that all states are affected in the same way? And then Virginia, I mean, I'm sure North Carolina has the same thing, and South Carolina too, but we have this Virginia Clean Economy Act, and it basically tells us when we need to be retiring units and when we can, or how much we need to build in the next 25, 30 years. And we have the big the company says 0 by 50, but the Virginia Clean Economy Act says 0 by 2045. So. Oh, the COVID impact. Everybody wants to know, what did COVID do to our load? So this is PJM's impact of COVID. And you can see it affected load a little bit, but really not significantly. We have so many data centers in Northern Virginia and DC area that the DOM zone load really did not see too much of an impact, thankfully. And we don't have time for this one, but you guys will have the slides later. So if you want to watch like a video of the PJM control room, you can get it in the slides later. So are there any questions? That was really fast, I'm sorry.
Okay, Jackie, so that was amazing. And this is from a former energy trader. I ran trading operations from 1984 through 1996. It was primarily gas, but we started into power. The complexity that you described with regard to the hour and daily offering markets is just insane.
Yes. Yes, so, hundreds of thousands of data points every day going to PJM.
All right, so an off-the-record answer, if you care to offer it. I'm sure that you have seen regulated utility markets operate, and you've seen the PJM hourly and daily markets operate. Can you discern whether one versus the other does a better job? And we're not talking about price, we're talking about allocating the commodity, making sure that the lights stay on. Do you see any difference?
Oh, I mean, making sure the lights stay on, no difference, right? Because, I mean, we've been reliable, right? So what I would say is the benefit of PJM is their size. So what's nice about being part of PJM is if I don't need to run my expensive units, I can easily get that from somewhere within PJM. So that's called power purchases. So I would say it's easier with being in PJM just because of the size. Yeah.
Okay, so a little bit easier maybe to maintain resilience.
Yes.
For a utility because of the ease of reaching out and pulling on power. Whereas in a regulated non-ISO market, you have all of these agreements, but you have to call on them as opposed to just the ease of you're just drawing from a market as opposed to calling up a neighboring utility and say, okay, I need this.
Right. Like I never have to call anyone to get my imports from PJM, right? It's just all automatic.
Yep.
Right.
Yeah. Okay. Good answer. How about anybody else has a question for Jackie? I'm going to use our briefest intro for Gary. As he's had a long and very active and productive career, but Gary's vice president for market development innovation with Hitachi ABB Power Grids. The company is actually a relatively recent occurrence, July 2020. And this position that Gary has is a little bit different than the one that he had with ABB, where Gary, I think you were with ABB for 20 years.
At least.
At least, yeah. And there he was responsible for all of their smart grid initiatives in North America, and is the general manager of the Smart Grid Center of Excellence in Raleigh. And typically we would meet him there and have really quite a robust presentation. So he has 30 years in T&D experience. Has been in Raleigh for a long time, and has had management responsibility in areas of strategic marketing, business development. Holds a BS and an ME degree in power engineering from Rensselaer Polytechnic Institute and an MBA from Carnegie Mellon. So Gary. Oh, and let me also mention Gary is one of our board members. And I'm particularly pleased to have him here as he every year decides on how to compensate me. Thank you, Gary.
All right, so why don't I get started? So David, thank you for the introduction and the invite to participate today. So my current title, VP of Market Development and Innovation. I support our business development activities across the utility sector in particular, and also lead initiatives around innovation and thought leadership activities. And I've been with the company with Hitachi ABB for less than a year since the company was formed last summer. It was the Power Grids division of ABB was established as a separate standalone company with 80% ownership of Hitachi and 20% ownership by ABB. But the division basically was moved out and established as a separate company. And we have products in the T&D space and power grid space, 4 different divisions, one being power transformers, another one being high voltage equipment, which would include gas insulated substations, high voltage breakers and equipment, capacitors, and that type of equipment. One is grid automation, which is software, communications, grid automation, distribution automation, substation automation, protection control. And then the last business being grid integration, which is HVDC, flexible AC transmission systems, power quality solutions, EV charging infrastructure, and those technologies. So why don't I get started? I have a number of slides. I don't necessarily need to use them. I want to make sure there's enough time for questions at the end in case anybody has a question. So I put together this deck just to introduce, the focus today around responding to greenhouse gas emission and pathways for greenhouse gas emission reduction, and then address some of the transmission trends, distribution trends, power grid edge trends, and then if I have time, I'll touch on some of the cybersecurity trends that we're seeing today. So try and keep this at somewhat of a high level. I can make the deck available to anybody who is interested in it at the end of the session. So if I go through the slides quickly, don't panic. If you're interested in any of the material, I can share that. So I see three main drivers in terms of power grid technology. This is where utilities are making investments today. And the first one is grid reliability and resiliency. And I would refer to this as, the fundamentals, it's blocking and tackling. Utilities have to be reliable, and with the changes that are taking place, particularly with the weather patterns of severe or extreme storms, they need to be resilient. They also need to be resilient as well as hardened against security issues, both physical as well as cybersecurity. So aging infrastructure is an issue, storm resiliency is an issue, but this is core to utility business. The second area of investment is the digital grid. And we break that down into three areas. We did some work a couple of years ago around the digital grid maturity curve and identified three main areas, those being digitization, going from analog to digital. Digitalization, this is really sharing, capturing data, managing data, and sharing data across the enterprise. And in business transformation, which is not only sharing the data, but actually using the data to transform the business and improve operational performance. And so we see the convergence of IT and OT technologies. We see the introduction of IIoT, the Industrial Internet of Things. For utilities, this really means software for control of the grid or analytics, it's connectivity, which is communications. We're seeing huge expansion in field area networks between substations and meters. And in devices, smart devices could be controllable reclosers, could be controllable capacitor banks, or other devices for power quality and voltage management. And in meters or sensors, so we're seeing those also being integrated and using the data from those. The other area is the global move to a carbon-free economy. This is really impacting utilities and the power grid space in two areas. One is being able to interconnect renewables, both at the distribution level, distributed energy resources, which would include solar PV, for example, but also utility scale, large-scale wind, large-scale solar, and being able to integrate those into the grid. And the second part of it is electrification. Our current focus is electrification of transportation. And it's really, power generation and transportation are the two largest sources of carbon or greenhouse gas emissions. So any initiative to reduce carbon has to address generation and has to address electrification of transportation. So this is just a chart that shows some of the challenges, the energy trilemma, looking at having reliable and secure power, also having a sustainable grid. This is really where the greenhouse gas emission reduction comes into play, being able to integrate the renewables, also supply the power for electrification, but also supporting energy efficiency. And we're doing things with eco-efficient products, for example, using synthetics for transformer oil, trying to find solutions for SF6 gas and high voltage breakers, et cetera. And then the third is really being affordable and optimization of cost. So in the lower right-hand, or excuse me, on the left-hand corner, you can see some of the UN Sustainable Development Goals, or SDGs. There's actually 17 of them. I'm showing 8 of them in this particular chart, which really are the ones that apply to more relevant for our business. In particular, items 7 and 13, which are shown, I guess the third one from the left, 7, which is affordable and clean energy. And then the other one is climate action, item 13, which is right below it, the green one. Those are extremely relevant for our company from a sustainability and social innovation perspective. And we are supporting, transition to a clean energy economy. And then the rest of this chart shows some of the technologies, in terms of the digital platform that I mentioned, the digital grid, and also establishing an energy platform. these are just the goals. These are the all 8 of them that we're focused on. You can look up on the UN website all 17. So I won't spend too much time on that. So a couple of other trends. One is the cost of renewable generation. We're seeing renewable generation now leading the investment of new generation technology in the United States. And there's a reason for it, just 2 reasons for it. One is it's now the lowest cost energy that's available. So the levelized cost of energy for solar and wind, they're shown basically converging as, if you look at the right side of the chart, out towards 2020, the 2 lines for wind and solar converge, and they're the lowest, have the lowest levelized cost of energy. So investing in renewable generation does not, you don't have to pay a price penalty anymore. And then the other advantage is it drives sustainability initiatives because wind and solar are certainly considered carbon free and also are renewable. So I think this is certainly a major trend. I didn't include the chart in this deck, but if you look at some of the Bloomberg New Energy Finance data, and you can go back into the late 1990s. And since then, the only new generation that was added to the grid, with one exception, actually 2 exceptions, but they were relatively minor in the overall scheme of things. The generation that's been added has been natural gas, and that was primarily in the 2000s when the natural gas was added. And as we went past 2010, over the last 10 years, we've seen wind and solar dominate. Now, some of those investment trends have been impacted by the investment tax credit, as well as the production tax credit. The investment tax credit was in place for solar, and the production tax credit was in place for wind. And policy does matter. So you can see some of the changes that took place based on status of those incentives. But clearly, as we move forward, we expect to see more wind and solar, and also natural gas will continue to displace coal as in the fossil fuel space. But I think that's also going to, well, it's either going to have to be cleaned or with carbon capture, or we're going to be replacing natural gas over the next 30 years as well. I'll talk about storage a little bit later, but you can see the dramatic change in the cost of lithium-ion battery energy storage. We're basically looking at an order of magnitude from 2010 till basically we're pressing now on $100 per kilowatt hour for lithium-ion battery energy storage, and in 2010 it was $1,000 per kilowatt hour. So you can see that storage has come down dramatically. And then also another emerging trend is what's going on with hydrogen, in particular green hydrogen. Utilities are looking at green hydrogen as a way to address long-term storage, seasonal storage. Also, you can transport hydrogen via truck and other options versus electric wires. And so it provides some flexibility and also enables better utilization of renewables when you produce green hydrogen. Again, green hydrogen, the definition of that is it's produced through electrolysis and using carbon-free energy. Now, some will argue that nuclear supplying that electrolysis process is green because it's carbon-free. Others will say it's blue, carbon-free, but not necessarily renewable. But anyway, we're focused on the carbon-free creation of hydrogen and how that can be used for power grids and the electricity landscape. So this is a chart that just shows, what we see as the future energy system with heavy emphasis on electricity, which we believe is going to be the backbone of the entire energy system as we move forward. In the green highlighting, you can see generation. On the left, it's bulk power, wind, solar, hydro, but we're also seeing nuclear playing a role, small modular nuclear. Canada's looking pretty significantly at that as a technology. So in today, nuclear in the U.S. is about 20% of the generation mix. But then as you move to you can see in the center, distributed generation, small scale solar, small scale wind. And then as I go from left to right, you can see storage. You can see dispatchable generation, which would be at the, again, distributed generation, could be combined heat and power, for example, or could be smaller scale on-site generation. And then you can see industry, transport, residential loads. And then at the bottom, you can see the introduction of hydrogen, pulling that from or driving that through electrolysis from green energy. And then you have the flexibility for storage, transporting it or feeding it into dispatchable generation resources. And so we see this landscape evolving, and we're focused on the renewable generation and the integration of that into the grid. We're also focused on supplying the power for electrolysis and/or fuel cells to convert the hydrogen back to power, focused on storage, and also providing the electrification for the key sectors shown on the right side. Just for your information, this is global. This is showing the overall energy trends globally. And you can see at the bottom, coal is basically becoming a smaller part of the overall energy mix. You can see natural gas above that. You can see nuclear sort of steady, maybe a little bit less than it was around the 1990s. And then you can see the growth of wind and solar. Just for reference, today, the US is about 40% carbon-free generation. Half of that carbon-free generation, or 20% of the total, is nuclear. And then the balance of the carbon-free generation is a combination of hydro, wind, and solar. Just for comparison, if you look to the north, Canada today is over 80% carbon-free, actually 82% if you want to be more exact. 60% of their generation is hydro, 15% is nuclear, and then 7% is the non-hydro renewables, wind and solar, just if you want to look at or have some of the local numbers for reference. But clearly the trend is moving to carbon-free, and most states and most utilities that are announcing for generation carbon reduction are targeting either net carbon zero by 2050 for generation, or 100% carbon-free generation, or the most difficult to obtain, 100% renewable generation. Oops, go back. So a few challenges that you have when you start to shift to the renewables, and I'll talk a little bit more about this, but one of the challenges, I guess there's two real challenges. The first is these resources are weather and time of day dependent, and they can't be dispatched on demand, which means renewable generation has a little bit of trouble following load, which is the way we operate the grid. We dispatch generation to meet the demand. And when you can't necessarily dispatch resources, you need to think about managing demand so that it matches up with the availability of these resources. The other challenge is the timing. Time of day can be an issue, when the resources are available versus when peak demand occurs, and then also location. A lot of renewable generation resources are located in the middle of nowhere, where there's no load, which means unless we build the transmission infrastructure, we can't connect those resources. And then the grid today is optimized for location of current generation. And when you start shifting locations, not only do you have the access issue, but you also create congestion on the grid, which impedes you being able to move the power. So if you look at some of the trends to address these issues, this chart's a little bit difficult to understand, but on the left side, you see conventional system operation, and then some of the challenges with high concentration or high penetration rate of, this says variable renewables, but basically wind and solar. And as you increase the percentage, which is the left axis of the chart, you can see once you get past 25% renewable, getting up towards 50% renewable, you start to see that grid congestion. You also need to balance your spinning reserves. You also need to coordinate your renewable generation with your baseload generation to make sure that, for example, evening peak demand can be met when solar PV is not available. And so that starts to constrain your dispatch and your utilization of renewable generation. As you increase and get past 50% and start to go to higher levels, you get into a concern around system inertia or grid inertia. And what this is when you have fossil fuel or thermal generation, the spinning rotor of those generators have inertia. And what that means is if there's a disturbance, that inertia keeps the grid stable for a period of time before the frequency will start to decay. So inertia is inversely proportional to frequency decay when there's a disturbance. High inertia means the frequency decay is slower. Frequency does decay. Once it drops below a certain threshold, you start to have generation and other devices trip off the grid, which is a bad thing. Power electronic energy resources do not contribute to system inertia. When you connect to the grid through power electronics, you don't have that inertia contribution. So wind, which connects through power electronics, it's generated AC, but not at system frequency. So there's a back-to-back conversion using power electronics to go from AC to DC and then back to AC at 60 hertz. Solar PV, you have a power electronic based inverter. And if you are supplying energy from battery energy storage or a fuel cell, you're also going through power electronics. So no contribution to system inertia. And then also short circuit capacity. Those power electronic devices don't contribute to short circuit capacity. This is important. If there's a fault on the system, you want to have sufficient fault current that your protective relaying will be able to operate and clear the faults. But you can see I highlighted with arrows some of the peak renewable energy, contribution to overall generation. You can see California ISO has gotten up towards 75%. Same thing with SPP. Also Texas ERCOT have gotten to pretty high percentages of renewables. By the way, the reason Denmark gets over 100% is they export their renewable energy into Europe. So there are solutions to those challenges. So this is a busy chart. But on the left, you see those same items that I had mentioned previously in terms of the challenges integrating renewables. And then across the top, you can see three areas: protection and control, demand and grid components, and then energy storage and generation. And you can see where the relevant technologies can help address the challenges. But it really comes down to a couple of key areas. One, when you have renewable generation, if you can't consume it at the point of generation when it's generated, then you really have to do, three things. So you can either store it, you can move it, which is transmission resources, to where there is demand, if it's not able to be consumed locally, or you can try and create demand by charging electric vehicles, for example, in the middle of the afternoon when you have a lot of excess solar, or the last option is you have to curtail it. If you've heard the expression spilt milk, which means it's lost forever, there's nothing you can do about it. If you don't consume renewable generation when it's generated, or you don't store it, or you don't move it, or you don't create demand, you end up with spilled kilowatt hours, lost forever, and it really does not help your business case for investment in renewable generation. So some of the transmission technologies that we support, HVDC transmission can go long distances, usually point to point with low losses. Also critical for connection of offshore wind once you go out past 30, 40 miles. The cables, AC cables have a phenomenon called charging current, because an AC cable, or any cable, actually is like a long capacitor. So the longer the cable, the more the capacitance, the more the charging current, the higher the losses with AC cables. You don't have that with HVDC cables. You can basically go hundreds of miles with HVDC cables and you don't have those losses associated with the charging current. So we're seeing more application for HVDC transmission to connect remotely located renewable resources. Also, if you want to move power from the Eastern Interconnect to the Western Interconnect or in and out of the state of Texas, which is its own interconnect, since they all have 60 hertz, but they're not synchronized, you need to use HVDC if you want to move power between any of the interconnections. Just the other technology, series capacitors. This is adding capacitors in series with long transmission lines, overhead transmission lines. Capacitors offset the inductance of the wires and means you can push more power through a transmission line. We've used those on long AC transmission lines throughout the country, including in Texas, on some of the long transmission lines moving power from Western Texas with the wind generation to the eastern load centers. Energy storage, extremely important. It decouples generation from consumption, also provides stability, can provide spinning reserve, it can provide frequency and voltage regulation. The size of the bubbles don't necessarily mean the size of the energy that's currently in service. It's a timing issue in terms of short-term minutes versus hours and days. On the right side, pumped hydro or pumped storage. It is our #1 energy storage capability or resource on the power grid. Represents over 90% of our storage capacity. Current investment today, though, is in lithium-ion batteries. SVCs and STATCOMs. This is basically static compensation. It involves managing what's known as reactive power flow. I'm not sure how many of you are engineers and understand reactive power flow, but basically it's like an insurance policy and it can inject or absorb reactive power to manage voltage. And it enables the grid to have a higher transient stability limit, meaning if there's a disruption, if the disruption is severe enough, the grid can collapse. And what a STATCOM does is it can inject reactive power, it can support the grid voltage, and it can give the grid time to realign its generation dispatch to recover from a disturbance without the grid collapsing. That's basically called relaxing the transient stability limit of the grid. We can combine a STATCOM with a synchronous condenser to address those issues that I mentioned in terms of stability of the grid, the inertia of the grid, the short circuit capability of the grid with high levels of renewable generation. This is particularly an issue in the UK, where they're basically retiring all their coal, which means they lose that source of inertia and shifting to wind generation. So we've actually installed one of these hybrid devices in the UK. And then I just included an offshore platform for wind. This is particularly interesting in North Carolina because we have, a lease area off the Kitty Hawk off the coast, which is targeted for wind energy development, I believe about 2.5 gigawatts. This particular platform is an offshore platform off the northern coast of Germany. It supports a 900 megawatt, nearly a gigawatt of power, HVDC converter station located on the platform. I think this is 135 kilometers from the mainland. So there's subsea cables that connect to the transmission grid that then feeds the power into Europe. I just threw this slide in. I just gave a presentation in collaboration with the Electric Power Research Institute, which has one of its offices actually in Charlotte, just showing some of the drivers as to why the eastern coast of the United States is a prime area for offshore wind development. So you can see the resource strength. You can also see that the mainland areas adjacent to the wind resources are high electricity prices. So it makes it easier to sell offshore wind, which might be a little bit more expensive because of the infrastructure which is required. Also shows that there's major population areas. And then on the far right, you can see locations of the different lease areas from BOEM, government entity responsible for managing the offshore wind lease areas. And pretty much all of those locations are in shallow water. So that reduces also the infrastructure costs. But these are the reasons why the Eastern U.S. seaboard is receiving a lot of focus. And President Biden just announced an initiative to facilitate the development of the offshore wind along the eastern seaboard. And also, I should mention that North Carolina Department of Commerce did sponsor a consulting study in collaboration with Virginia and Maryland, looking at the supply chain and supply chain readiness to help support offshore wind development. So state of North Carolina is also looking at this. So distribution technology trends, I'll just touch on these briefly. This particular chart just shows a breakdown of the landscape of distribution grid. In the center top, you see the energy trilemma that I talked about previously: reliability and security, being affordable, and also being sustainable. In the two red circles, you have the control room and the operations center in the upper right-hand quadrant. This is really the nerve center of distribution grid operations. And then also in the lower center, that other red circle shows some of the distributed energy resources which are being interconnected to the grid, as well as customers. So you see, small scale wind, you see solar PV, you see energy storage, you see EV charging infrastructure. Also, demand response is being implemented, technologies for automated switching, automated volt and VAR control to manage voltages on distribution circuits. All of these are devices and resources at the distribution level. So I want to focus a moment in terms of the distribution control room, because this is really, at the center of the distribution landscape. And this is where a software system called an ADMS system, which is Advanced Distribution Management System. This is really the tool that the dispatchers and grid operators use to manage the distribution system, both during blue sky operations, keeping track of status of operations, managing the crews that are working in the field, and really driving situational awareness. They know status of the system. They know if there's also any outages scheduled or otherwise. And it's a graphic user interface, computerized digital representation of the grid, and it's the tool that's used. It also includes advanced functions such as automated switching for reliability purposes, which is part of storm response. Also includes volt-VAR optimization that I mentioned previously for managing distribution feeder voltages. It becomes a real challenge when you start piling on more solar PV and having all the inverters tying into the grid along distribution feeders. It can be more challenging to manage and maintain both protection and control, but also voltages on distribution feeders. But that situational awareness becomes particularly important during storm response, being able to manage the crews, knowing what's out of service, what the cause of the outage is, what the repair requirements are, and more importantly, being able to tell customers and all the other stakeholders status of outages. Being aware that a customer is out of service, but also being aware as to how long an outage will last and when a customer can expect to have service restored. Critically important. I think the utilities in Texas struggled a little bit with their big winter storm that occurred, trying to provide information to customers who were either out of service because of the storm or were being subjected to some of the rolling blackouts, which I think at times were not necessarily rolling, and customers were losing service. And having that situational awareness is critical in terms of your distribution operations. The other thing that's also part of the control room software and tools, because it uses the same network model. Network model is the connectivity and impedance model of the grid, which is used for running simulation tools and analysis like load flows so that you can model the system and its operation. So part of that is distributed energy resource management system, or DERMS. which is really an overlay of the ADMS system and extends it to be able to manage distributed resources. So you can see the 4 key elements of this in the center. They have numbers on them, but I pulled this from another presentation that somebody else gave, and I think the numbers are out of sequence. So I would put the first component on the left side, hosting and registering distributed energy resources, so you know what's out there, particularly so you can host them in terms of connecting them to the grid, but also registering them as a controllable device when they are subject to aggregation and can be controlled to offer grid services. The second is the bottom, which is managing the distributed energy resources and optimizing the deployment of these resources, doing a day-ahead scheduling, for example, of the distributed energy resources, and making sure that the grid can manage it both locally at the distribution level, as well as when coordinated and aggregated at the overall system level. Then actually dispatching, which is shown at the top, dispatching and managing that control. And then the last part is market settlements and managing the transactional part of managing distributed energy resources, which is shown on the right-hand side. But we're seeing development around distributed energy resources and the growth in that. There's been some FERC orders addressing distributed energy resources, FERC Order 841, and then also FERC Order 2222, which address some of the aggregation and ability to offer grid services of distributed energy storage and also other distributed energy resources. So just touching on Grid Edge, these are some of the microgrid technologies. And what you can see is in the dark shading is basically a new layer of digitally enabled solutions to address some of the challenges that we're seeing for stakeholders along the value chain. This would be system performance optimization, looking at grid reliability, and being able to offer energy services. So we're seeing, microgrids with storage, introduction of, software as a service being offered to utilities. We're seeing more cloud-based solutions as business models change, and we try to leverage the distributed energy resources and expand the digital services, solutions, and technologies which are available. So this next slide pulls up. When you look at the red arrows, you can see the functions and applications organized by starting at on-premise at the bottom and then moving up through to cloud-based solutions and the advanced applications which are shown at the top. If you look at the left side, you can see the different functions or applications. Focusing on energy storage, battery energy storage is typically a component of all microgrids that are being implemented. We're even seeing battery energy storage being used with EV charging infrastructure for fleets to be able to manage demand and reduce impact of the charging infrastructure to the grid. Control, being able to manage the distributed resources. SCADA, which is a supervisory control and data acquisition. Energy management, which is really optimizing local energy consumption, just using EV charging infrastructure as an example. Again, how you manage the charging, how you minimize peak demand, how you take advantage of lower tariffs or time of use rates to do that energy management and optimization at the premise level. And then moving up through monitoring. And then at the top, you can see the various applications in terms of analytics, optimization, service and maintenance, coordination and optimization, and then overall control and management, including management of multi-sites and coordination of those. One of the growing areas that we see, part of the changing utility business model, partly driven by seeing more and more distributed energy resources and recognizing that behind the meter resources can be aggregated and deployed for grid services. Just I have a slide on energy storage. Again, key element of grid operations for shifting load, taking and storing surplus renewable, discharging in the afternoon, providing peak shaving, providing ancillary services like spinning reserve, voltage and frequency regulation, and being able to also support islanding. One of the things you can do with a microgrid, if you have, as part of the microgrid, you have renewable generation or other on-site generation that can be dispatched. You can island from the grid and operate with the generation resources. If those generation resources do not include, for example, diesel, battery can actually be the grid forming device, and it can maintain the voltage and frequency, allowing an islanded system with renewable generation to go to 100% renewables. Particularly important for island communities that have to rely on diesel generation and renewables, and they want to get off the diesel generators as much as possible. That becomes a useful function. But stacking of the applications of renewable generation is a key issue for the value proposition for renewables, and something we're seeing more and more of. This is just an example of an islanded system, which is normally grid connected. When it is grid connected, it provides grid support and also enables the feeding into the main grid renewable generation from both wind and solar. However, if there's a disconnect from the larger grid because of a disturbance or event, in this case, this 30 megawatt battery can actually act as the grid forming device, and it can keep the grid operational and functioning and minimizing or eliminating outages for the customers who are served by the islanded system. When the grid is restored, it can seamlessly connect back to the main grid and continue to provide renewable generation and stability support to the grid. So the capability of the power conversion system of the battery to be a grid forming device provides added value and also grid flexibility. I won't spend too much time on cybersecurity. Just wanted to touch on this. We're seeing more focus on the value chain. This is a white paper that was actually done by the World Economic Forum. The first section of this basically focuses on drivers of change. Second phase of the report is focusing on roles and responsibilities, and then key findings and reflections on securing the value chain. Big effort in the United States in terms of looking at supply chain and cybersecurity issues related to supply chain. And it's just key focus areas. One, looking at the product supply phase. This is really the supply chain and looking at the cybersecurity threats and practices of suppliers to mitigate that. Looking at the design and commissioning, particularly when you have local automation, whether it's an industrial process or whether it's for the grid. But commissioning and the design of those systems is critically important to maintain cybersecurity. When you get to the operations phase, which another key component, securing operations, and then making sure that there's product support and security support through the handoff, starting with the product supply and going through the operations phase. And this is highlighted in that white paper, but something that we see a fair amount of. So this is my last slide. We believe that electricity is going to be the backbone of the entire energy system. We expect to see energy consumption may be flat, and if we're real good with efficiency, maybe we can actually reduce total energy consumption. But the percentage of the energy consumed, that is electricity, is going to grow. And a case in point is electrification of transportation. As we electrify transportation, we could see growth in energy delivered 25 to 40%. So in-use electricity growth is going to be key. And so we expect to see electricity be key as we go forward. Also, as we go to a clean energy economy with the renewable resources being located away from location of consumption and end use, we see the electric grid connecting the wind, solar, the hydro, modular nuclear resources and moving those to the end use. So somewhere along the energy consumption stage, we expect to see electricity. And even if there's hydrogen, electricity is going to support green hydrogen, and that can either be stored, dispatched for generation, or used for end-use applications like long-haul transportation. So just some fun facts: electricity demand going up, electricity is more efficient as an end use, and we see all market sectors converging towards electrification. Ultimately, we're trying to reduce greenhouse gas emissions, and hopefully that will have an impact on climate change and reduce the number of severe and frequent storms that we're seeing. And so I don't know if I have time for questions, David. I can take a few questions if anybody has a question. And I'll leave this up for a second, just in case anybody has a follow-up question they don't want to ask. They can send an email and contact me.
Gary, you do have time for questions. So if anyone has questions, please unmute and pose them now. Okay, Gary, I've got one while they're thinking. So in the course of your presentation, you covered a lot of technology that that can address new uses. You've talked about hydrogen and vehicles, and so when you look out over the landscape right now at the grid edge, where do you see the majority of the activity occurring right now, and how do you think that's going to change over time?
So in terms of looking at grid edge, I think we're seeing a few things occurring. One is you're seeing more communications infrastructure being deployed at grid edge, and this is to provide a communications capability or connectivity between substations and meters. So utilities can read smart meters, they have those communications in place. And then also most utilities have communications to substations, but the void between the substation, not the void, but the equipment between the substation and the meter is becoming critical infrastructure, particularly as utilities become more sophisticated in responding to storms, become more sophisticated in terms of hosting EV charging infrastructure, hosting distributed energy resources like solar PV, and being able to maintain the security, being able to maintain the voltage, being able to optimize the efficiency and have flexibility to host growing amounts of solar PV, EV charging infrastructure, integrating demand response. There's a lot of activity and investment that's occurring at grid edge. That said, I do believe we're going to see an awful lot of investment at the transmission level for the reasons that I mentioned, that a lot of the new renewable generation is going to be utility scale. And there's been studies looking at transmission investment that says for every dollar invested in transmission investment, there's a $2.50 payback. NREL, the National Renewable Energy Lab, did a study. They never published a report, but it's called the SEAMS study, SEAMS. And that's looking at providing transmission capability to move power east and west across the country. Has a component of HVDC to get across the interconnect between eastern and western US, but also it has interregional transmission to be able to, again, provide access to renewable generation and then reinforce the grid to reduce congestion to be able to get power from the source of generation to load. And that added flexibility means we can have higher levels of renewable generation, which has economic value. So I see both, David. I see grid edge for the reasons that I mentioned, but I also see transmission as being a critical component of achieving our greenhouse gas emission pathway reduction. So certainly grid edge in terms of some of the digitalization that we're seeing on the grid. That also applies to transmission, but the interconnection of renewables is important, hosting on distribution circuits, but also at the transmission level to be able to facilitate that growth.
Gary, Yeah, that's fine. Do you have any concern about the grid edge infrastructure and the rapid adoption of electric vehicles, both passenger and commercial?
So the answer is yes. But a couple of perspectives. I mentioned that NREL did a study where they expected the number of kilowatt hours to be delivered, the amount of energy to be delivered could increase by as much as 25 to 40%, particularly as we look out towards 2050. That's not necessarily a problem if that added energy is not delivered during peak demand. So if that energy can be delivered at some point where it's not coincident with peak, there's enough capacity in the generation, there's enough capacity in the transmission grid to be able to deliver that energy. So two issues have really emerged around EV charging infrastructure and the charging of the growth in electric vehicles. And the two components are called make ready, which is, can the grid accommodate the added load, which is the question you had. And the answer is yes, although there may be some investment that needs to occur at the local level, because there's an issue around demand of, for example, for fleet charging. There's an issue as to how big does the pipe need to be to feed the facility. That's really the T&D infrastructure. And then if that pipe, what is the peak demand that needs to be delivered to that facility that's coincident with the overall system peak? Because that's going to drive generation investment. And so those two things, non-coincident peak demand and coincident peak demand, are really what are the issues around the grid make ready. And trying to mitigate those as much as possible means you may not have to invest significantly in the grid. Then there's managed charging, which is as a grid or an EV charging infrastructure owner for, let's say, again, use fleet charging as an example. How do I minimize my impact to the grid? How do I make sure that I minimize my peak demand, both occurring during the system peak as well as just my overall peak? So maybe I install a battery at my facility so I can manage my peak demand better, or I schedule my charging such that I only charge my vehicles when they're, when the rates are low off peak. And so managed charging is another key issue. New York, which is somewhat aggressive regarding electrification of transportation, has allocated $700 million to the utilities in New York to address the grid make ready. And then, of course, on the EV charging infrastructure side, it's going to be the fleet owners, the facility owners, who are going to want to manage their facility to minimize the demand charges and to minimize their impact to the grid, because it'll save them money.
So what I hear is that the rise of EVs may prompt as much software communication and knowledge management as what it does hardware to grid edge.
Yes, there's a lot of work that's being done looking at charging infrastructure patterns. When do you charge? If you take, for example, the organizations like Amazon, FedEx, UPS, which are looking at electrifying their last mile vehicles, where you charge those at some depot or a warehouse, you also have, package sorting equipment. So you need to make sure that you're coordinating those loads and, having information about vehicle, miles driven. You also need to design the vehicles. How big of a battery do you put in? What's the dwell time when the vehicle's available for charging? And then how do you manage those loads to mitigate your impact to the grid, and then still optimizing the dollars that you spend on the actual charging infrastructure itself? So yeah, there's a lot of analytics that are involved. Telematics of vehicles, charging patterns, monitoring and measuring and monitoring the charging infrastructure. All of that is driving analytics in the transportation space. Not that that's being done today with internal combustion engines. All the major trucking companies, closely monitor their vehicles, and use the vehicle telematics to optimize, for example, maintenance on the vehicles.
There we go. Everybody's looking at a beautiful purple screen. All right. Now, I'm going to take you back to some of the concepts that you covered, I think it was last session when we looked at rates. You had a rate class. So first of all, we're going to revisit the way that it was. So this is history. It used to be that regulated utilities generated all the electrons. They, through transmission, they moved all the electrons, and then they distributed all the electrons, and all the electrons produced were consumed by the end users, industrial, commercial, residential. Excuse me. And as a result of that, all of the dollars that the consumers spent on electricity and related activity, all of the dollars moved back through that chain to the utility. Now, this is the historic regulated utility business model. And this business model arose from the initial development of this industry, primarily in congested city areas where multiple power generating companies ran multiple lines. You can see some of the pictures. You go back to the old black and whites where there's literally 3 or 4 different competing systems of poles, and each of them have dozens and dozens of lines, and it's a mess. And what happened over time was that the states took control of this. They began to regulate the utilities in a fashion where they allowed them a regulated monopoly, because at that time, creating a regulated monopoly was the most effective and efficient means of investing the capital and delivering the electrons as that industry evolved. So we're going to take a look at what's going on today. All right, here's where we get to your rate class. And we're going to simplify what you heard very much. What you heard was that there are certain classes of expenses that get treated differently in the rates. So for example, what you heard was that fuel gets loaded into the rates as a pass-through. In fact, in some instances, there's a tracker that just basically says, here's your cost of fuel, and we just pass it all the way through to you as the consumer and allocated it in the manner agreed. We heard that operating and maintenance cost, there's an historic analysis. That analysis is debated upon by the various stakeholders. Eventually, the utilities, the stakeholders, the regulator, they settle on what is the total pot of O&M dollars. And then the O&M dollars are apportioned out to the various customers based upon agreed upon formulas. And then we found that there was capital. 2 types of capital. One is debt. Debt was pretty straightforward. There was an analysis of the debt portfolio that the utility held, the various types, the lengths of years for which the debt extended, the different rates, the overall cost of that, and the cost of servicing the debt and amortizing the debt put into the rates. That was a portion to customers. And then finally, the equity portion. And with regard to the equity portion, there was an analysis as to what the fair return is on equities, on the utilities' equity portion of their capital portfolio. So this is the stock. So what does the stockholder get after all of these costs are covered? Typically has been in the 10-11% range the last few years. So what happens is these costs are all added up in the rate case. They're apportioned by formula. They're spread over the design volume. And the design volume is the volume that everybody has argued through and agreed upon that the customers are going to consume going forward. So the utility rate case gets settled. The rates begin to be charged, and let's assume that the design volume is met. So what happens is that as the costs come in, fuel is paid, O&M is paid, debt is serviced first. And what's left over is then available to distribute to the company's shareholders. Now, hopefully it works out just like this, so you get a 10% return on the equity investment. However, if O&M, for example, is more expensive, the utility's return is going to be less because they're only going to get so many dollars. If O&M is a little bit less expensive, the utility might actually make a little bit more money. But over time, this O&M element gets washed out because every time the utility goes in for a rate case, the efficiency that may be realized from this O&M that provides them more earnings gets taken away from them. Because O&M looks back to say, how did you do? And we're going to base your O&M charges upon your history. Now, the other aspect of this is that all these costs have to be just, reasonable, and the capital expenditures have to be for capital physical facilities that are used and useful. So let's take a look ahead and see what happens here. All right. Now, the elements that are beginning to upset this model are threefold. One is that the utilities, if you think about this equity element, if a utility's earnings are going to grow, it's going to come from the return on the equity portion of its capital portfolio. Now, the rate of return is fixed in the rate case. So if a utility's earnings are going to grow from its regulated operations, its equity investment, its capital investment is going to have to grow. And where does a utility spend capital? It spends it on generation, transmission, distribution primarily. Now, there's some capital expenditures on rolling stock, vehicles, and things like this, buildings, but the big expenditures are generation, transmission, and distribution. Now, what we're seeing when we look at this chart here is we're seeing the utilities historic. So here's, let's see, this is 2018. So here's the projection for 2020 right in here. So here's the utility industry's projection as far as how it's going to invest capital in electric generation. And you can see that back in these years, the blue is primarily natural gas. The gray in here is wind. So you can see that there was a fair amount of wind investment in these years. And then only about 2011 do you see yellow, solar, begin to become part of the stack. But you also see the line down below here is where the utility industry is retiring generating assets. And you see that these retiring generating assets are primarily natural gas, aging natural gas plants, coal, aging coal plants, and then you get a little bit of nuclear in here, which is this light blue. Okay? Now, you can see in some of these years that the amount retired exceeds a little bit than the entire capital investment in generation. So in that year, capital investment portfolio net overall shrunk. Now, another thing to factor in here is that starting at about this point, right after the year 2000, not all of the generation that's in our national generating portfolio is owned by the utilities. And over time, an increasing amount is not owned by the utilities. So for example, this gray that you see in here is, for the most part, it's wind, is not owned by the utility. So it does not go into their capital portfolio. It's owned by third parties, or if the utility does own an investment in wind, it's primarily with their non-regulated subsidiary. So if you step back and say, well, this light gray is not part of a utility's generating portfolio. And then if you further look at the yellow and you say, well, for the most part, solar is developed by third parties, so the capital investment is with third parties. You begin to see a whole different picture here. So let's look at this stack that sits right here where my cursor is. So you see a lot of solar, a lot of wind, a little bit of natural gas capital investment, and you see coal retirement and natural gas retirement. And this stack below the line is bigger than what probably is the utility stack above the line. And if you begin to examine the trend forward, you can see that the utilities are becoming less of a factor in making capital investment in generation. So here's the first threat that we see to this historic regulated business model that's been driving the power industry. We see that it's not able to invest as much capital as what it had been previously, because we now have third parties investing in wind and investing, in out years, primarily in solar. So there's one threat to the business model. There's a second threat. So what historically has happened is that this bottom line is the 30-year Treasury yield, and you can see that it very closely follows the utility return on equity, which is the top line, the blue line. And what happened back here in the 90s is that there was not much of a spread. So if this dark blue line is the proxy for the cost of capital, and the light blue line is the return, you can see that the difference between the utility's cost of capital and its return have widened a little bit. But what's happened in recent years is that this relationship has flattened out. It's no longer expanding. It's flattened out. And we're beginning to see a little bit of an uptick where this is beginning to narrow. So at the same time that utilities are not able to invest as much capital as what they had historically, they're also seeing the spread between what their return rate is and what their cost of capital is narrowing a little bit. And they're seeing downward pressure on their historic rate of return. You can see for the first time it's dipped down below 10%. And you can see here, South Carolina, November 2019, there was a 9.5% return rate proposed. In July 2020, this past year, in North Carolina, 9.75% rate. So we're seeing pressure on the rate of return, second factor. The third factor is that we have historically low load growth. So you can see that back after World War II, electricity growth far exceeded the GDP growth. But in the 90s, there was a crossover, whereas the economy continued to grow at a relatively modest rate, about 2.4%. But as a result of efficiency that's being increasingly built into the consumption side of the power market, you're seeing that demand growth has become exceptionally low. Less than 1% per year is projected from 2020 out through 2040. Let me ask you this. If you have a business and you're the business owner and you're going to the market and you're going to sell stock to raise capital to continue to invest in this business, and if you say, shareholders, I have this great deal for you. This is a fabulous deal. So I want you to buy this stock and my market grows, get this, it grows at 0.9% per year. And oh, by the way, my return rates are drifting down and I have less and less opportunity to invest capital. So how about it? This is a great investment, invest in this stock. So, again, a third factor that is challenging our historic regulated utility power model is low load growth. Now, what are the utilities doing about it? So again, we're going to go back to this question of capital. So if we look over here at this chart in the top right, you'll see here's the industry's historic capital investment, you'll see that, we're coming up close to 100 billion. Let's say we're at 90 billion, kind of average this period right in here, about 90 billion. And you look over at this top left chart, and this is where the utility industry has been investing in transmission. And you can see it has, this is a 20-year period. It has really accelerated its capital investment in transmission. We went from, let's say, 3 up to $21 billion. That's a 7-fold increase. So now we're up to $21 billion out of this 90. So if we're going to stay on par with this 90, then distribution and generation has to come up with another $69 million. Okay, so let's see what they're doing here. So we come down to down to distribution. Distribution has grown from, let's call this 14, let's call it 13, up to, let's call it 18. So we've had a $5 billion increase, but this is over about 18 years. So we don't have nearly the trajectory in distribution capital investment that we see in transmission capital investment over the same period. So on the distribution side, the utilities are not doing as well. So we've got $69 billion that we have to cover just to maintain status quo, let alone grow. But here, we're only covering, let's call it 18 billion a year. So out of that 69, now we've got 51 billion, a lot more than half that's got to be covered by generation. And as we saw back here, what's happening with generation? Come on, generation. There you go. What you see here is that a majority, a little bit better than half of capital investments are expected to be solar going forward. The blue in here is primarily combined cycle natural gas. And that we know that a majority of this grid scale solar is going to be developed by third parties. So when we think about the utilities trying to find ways to increase their capital expenditures, you look at distribution and you realize that the utilities have to change this profile to where it begins to ramp closer to what we saw with transmission past 20 years. And the utilities are attempting to do this. So this is a focal point, invest in distribution. And you just heard Gary talk a lot about the potential to invest in distribution. This gives you some idea as to where there are grid investment initiatives going on. You'll see that the states that are dark have 10 or more actions, and these actions can be studies, investigations, rate reform, incentives, actual deployment of new grid technologies. So you see that there's a number of states where the utilities and their stakeholders have been successful in creating initiatives to make greater investments, greater capital investments in the grid. This, however, shows you the projection of solar deployment. All right, so if we stand back and we think about generation and where the investments are going to be, what we saw was natural gas on the rise, coal being decommissioned, nuclear relatively steady state, and non-hydro renewables, in other words, primarily solar and wind, on the rise comparable to natural gas. So even at a macro level, when we stand back and look at it, we say, okay, the utilities are going to make capital investments up in this area with natural gas, and third parties are probably going to be here with the non-hydro renewables. And if you take a look at the levelized cost of energy for these various types, what you find is that grid scale solar that provides alternating current to the grid is very cost competitive. Hydro is very cost competitive, but will not have any new hydro built just because of the environmental challenges of building a new reservoir. And then you have gas combined cycle, and then you have land-based wind. But land-based wind is going to be fairly limited in our service area. So you're going to see offshore wind, which at presently is not very cost competitive. Here's a look into the future, 2030. And again, you get somewhat the same picture. Offshore wind still stays relatively expensive compared to land-based wind, grid-scale solar PV. Here you have a distributed community solar, distributed residential, a little bit more expensive. And then here's gas combined cycle. Nuclear, even the small modular reactors and the new designs are still a little bit of a question mark, and you can see that they're priced noticeably higher than gas combined cycle. So again, everything we see tells us that the next decade, the decisions are going to be between gas combined cycle and primarily solar, grid scale solar PV that produces AC current. And the solar is going to be primarily the domain of third parties, with combined cycle natural gas being the investment choice for utilities. All right, so here's the third initiative that the utilities are taking to react, and that is to electrify everything that's fossil powered right now that can be electrified. So vehicles obviously is a focus, but when the Energy Information Administration looks at this and they take a look at, this is their annual energy outlook for 2015. If we take a look today, it's still fairly representative. And what we saw was that if the utilities are able to electrify everything reasonable with regard to heating and transport, that there'll be about a twofold increase in the consumption of electricity. However, if distributed solar realizes only 50% of its technical potential, what we find is that there'll only be about 10% growth as opposed to a doubling, because so much of the power generation has moved behind the meter. So the utilities are no longer handling those electrons. And if we realize even more, say 100% solar distributed generation technical potential, the demand for utility generated electrons actually goes down. So you can see that there's a real question mark with regard to the initiative for electrification. Utilities obviously have to move to electrify heating and transport just simply to offset the potential for distributed solar behind the meter generating electrons and taking sales away from the utilities. So a quick question with regard to, does natural gas and the ease of deregulation there tell us that we should look at deregulating the electricity market? And the markets are really different. And the difference is that when the natural gas market was deregulated, the utilities did not own production like the electric utilities own generation comparable to production. The natural gas utility industry owned primarily transmission and distribution. And also, natural gas could not reasonably be produced behind the meter. So today we have two different industries here, with the electric utility industry owning a good deal of generation and realizing benefits from the continued capital investment there, and also the prospect of a good deal of electrons being generated behind the meter, taking demand away from the utilities. So some big differences between how natural gas evolved and how electricity is going to evolve. And here's just some examples presently of the companies that are hard at work either reducing demand or creating electrons that are consumed behind the meter that no longer require electrons to be generated, transported, or distributed by a utility. So what needs to happen? Well, a lot of that's being discussed right now. The utilities, as we saw, are increasingly diversifying their capital investment back to distribution and transmission. Innovative utility rates are being investigated and tried out, demonstrated. Utilities are being rewarded for non-electron services. So they're being rewarded now for things that they don't invest capital in and get a return on. Or they're being rewarded for not selling electricity. In other words, energy efficiency innovations, things like that. And people are beginning to try to figure out how do we reward the utility for providing the backup service when we see a good deal of sales erosion occurring behind the meter. But the bottom line is that there's still no solution for this. So the utility business model is still in transition. It's experiencing some challenges right now, and literally every utility that is a regulated utility in the United States is dealing with these issues that you just saw, and we're going to see various trials over the next decade. So you are the group that as you move up the management ranks and you're on the power side, whether you're a supplier to a utility or whether you're with the utility itself, you're the ones that are going to be dealing with these large scale issues, figuring out how do we provide resilient, reliable service to our customers, but also provide a fair return to our investor-owned utility shareholders. So let me stop there, see if anybody has any questions with regard to what I just covered.
Hey, David, it's Marcus. Quick question. On slide 11 and 12, I was kind of shocked to see coal on there as much as in years out. Could you talk a little bit about that, if you don't mind?
Yeah, so there will be no coal built. If you saw coal that's in the mix in the out years, it's probably an error in the slide, or it's just a misread of the color. What you're going to see in the out years is maybe a little bit of nuclear 10 years out, combined cycle natural gas, and a little bit of wind and a lot of solar. I'm going to go back to screen share. I'm going to see if I can quickly get that slide back up so we can take a look at it. And it's not coming up easily. So while I get that up, let me see if anybody else had any questions for me.
Thank you.
Okay, so we were looking at this one right here. Marcus, was it this one or the next one?
Yeah, we saw coal kind of decline in there you talked about, but if you go to the next slide, I think slide 12, you'll see where you still have quite a bit of coal there showing.
Oh, now what this shows is it shows you the price range if you build new coal.
Okay.
Yeah. So it's not saying we're going to build this much coal. What it's saying is if you build new coal, this is what's going to cost you.
And slide 13 is levelized in 2030. I think that's where I got confused.
Yeah, that's right. So if you build new coal, this is what's going to cost you, and it's relatively expensive compared to some of the other sources.
Okay, perfect. Thank you.